Really great to see you. I hope you can hear me all the way on the back side there. Yeah, okay. So I'm Sven. I'm in the top management of Schibsted, heading data and technology in Schibsted, and I'm super pleased to see so many people joining us here today from all over Nordics. So in short, why is personalization and recommender systems important for Schibsted? The first thing I think is we have to admit that users expect things to be personalized. They want things to be relevant for them, and they want to be guided in an abundance of content. It doesn't matter what kind of service you're in, it's just abundance. So how do you actually give people a good experience? The second thing I think is really about the lower friction. And sometimes when we in Schibsted talk about our marketplaces, you know, it's always cool to know that people spend hours and hours inside of marketplaces looking at different things, but some people don't like to do that. They like to go in and they like to try to find something fast, and they want to do a transaction and then want it to be smooth. Then we think also that it's super important that we actually are good at doing recommendations, so we can lower the friction for the users. Then there's also a part of this which is about competition. And we are, as Nordic companies, up against global competition in lots of our different areas. And they have vast resources in performing these kind of features for their customers. So we need to be on top of it. That's for sure. And particularly, I would say in media, we have a special situation where we are editor-based media, whilst users, particularly the younger users, are using social media, which is highly personalized media, which they are really expecting. And I guess you can talk to, if you have kids, you talk to them and you ask them, you know, why don't you read newspapers? And if you read newspapers, well, Dad, why on earth am I getting news about soccer all the time when I'm not interested in soccer? It's a very good example from my daughter myself. Then I think it's the last one, and we need to talk about business. It's good for business, right? We get higher engagement. We get people to stay on our services. We get them to actually find what they're looking for, and that we get higher transactions. And that's super important for business. So it's, there are many folds why it's important for us. So we focus a lot on this in Schibsted. We've done that for several years, but there are certain parts of Schibsted where we are been focusing more in the last period of time. Then I also have a role. We have a chairman in one of the research institutes in AI in Norway. It's called Norway AI. It's a part of NTNU, where we're working with language models. So we're working with LLMs. First of all, we've started and are now training, soon finalizing the 24 billion parameter on Norwegian, which is going to be then on the level of the Swedish one. We are talking to Sweden AI about working together with them, because we think that there are better performance when you mix Nordic languages. And we are just applied to the EU together with the Fraunhofer Institute in Germany to make a Germanic language model. So we are also involved in the research side of it, as we are a large holder of content, because our journalists are producing massive amounts of content, and there's a lot of content also on our marketplaces that can be interesting for being the data corpus for making LLMs. So it's great to see you all here. I think it's super important. We are small countries, small companies globally. So much is happening within the space of recommender systems and personalization, not at least on AI. And I think no one really feels that they have, you know, everybody knows what's going on. This is not moving so fast. It's moving extremely fast in a lot of different areas. So actually talk to others, hear what they're thinking, how they're reflecting upon things, and what they know is a super important part of actually being updated within our fields. So welcome, Simen, you're going to guide us through the day, and give him a hand.
All right, super great. Great to see you all. I would say, like, when we started to talk about planning this. Oh, you want? Okay, yeah. I was a bit sure, like, I was thinking, like, okay, let's make this recommendation or personalization day with sort of academics and industry meeting with those working. I was like, maybe we will bring 40 people maximum, like get a small meeting room kind of to do it. And I think Arnoldo, I think you said like we need 300, like we need a room for 300 people. I was like, oh no, there's no way it's going to be 300 people. But I think actually you were right, because we have been having waiting lists to join, and I had like the very difficult choice of saying no to people, which is not something I would assume for such a technical field as personalization. So that means that it's there's a highly people are interested in this topic. It is an important topic. It matters in very many people's lives. But unfortunately, we were not able to get everyone. But I do hope that the ones you are here, like you are highly into recommender systems, you know what it is, and you can sort of work on it. And that's sort of part of the goal with this, is not only to have talks, but the idea here is that we have talks, we have fairly short talks, but then we try to have coffee breaks and discussions going. So that's sort of the idea behind this. Like, this is a meeting place for us to meet, so that we can talk about these things and not just talk about like ChatGPT all the time, which I think most of my time is doing. Is what I'm doing. Good. I have some practical information. So first of all, like, is the sound good? Like preferably we want to do it without a microphone, but like people in the back, are you good? Perfect. So if there's any problems, we can turn on the microphone, but we'll try to keep it off as long as possible. There's some emergency exits. So there's the entrance you came in, and there's an emergency exit here as well. Then you come up in sort of the closet where you left your clothes. Toilets is also in that area, so you go up and they're like in the locker room. We have only 2 toilets, but hopefully that will be enough. And yes, and we have some students from Akademia High School that are here to film the talks, which we are really grateful that you are here. So give them some applause. Because we realize that there might be more people than those of you in the room right now that want to see this. So we want to record that for later. That means some like practical privacy concerns. I mean, we will only record the one who is talking. But if you are moving around and these kind of things, you might enter the video feed, right? So I hope that's okay. But if you sit still, you will not be recorded. That's the idea. For the speakers, when you start talking, not like I did, but then you will get this mic just when you enter, right? Yeah. And if you're a speaker and do not want to be recorded, just tell us before you start speaking, or tell Joachim here, this guy, just before you start speaking, and then we will not record you. Good. Yeah, and I think that's it. We have a long program. I think it's going to be a long day. I think it's also going to be a very rewarding day, because there's I think also like in the beginning I was a bit afraid like will we get enough talks, but I think like looking at the program now there's a lot of great talks from a lot of different people. So I'm really looking forward to that. And then after we will have some lunch. We will have lunch. We'll have breaks and all these kind of things. You can see the detailed schedule on the site. But yeah, and then we will have some drinks after if you want to join us for that up in the cafeteria of VG. So good. So the only thing that remains is to invite the first speaker, which is James Grant, which is coming all the way from Lancaster to tell us about Bandit's exploration, exploitation dilemma. So welcome, James.
And yes, so thank you very much, Simen and the other organisers, for inviting me from all the way from England. So it's really, really nice to be here. I've been to Oslo a few times, but not since the pandemic. So it's very nice to be back. And today, so I'm going to talk not explicitly about personalisation today. I'm going to talk, as Simen says, about bandits and exploring within recommendations. And the first thing I'm going to do is make my title a bit simpler than it was on reflection. A more concise title would have been this idea of exploring during the process of making recommendations. So the whole thing today is going to be kind of something that is cross-cutting across various ideas of personalization and recommendation. Some of you will have seen these ideas before, some of you maybe won't, so it will be quite a light, accessible talk, but hopefully, even for those of you that have seen this kind of stuff before, you might take something, a different perspective away from it. So, I want to start by looking at the kind of very, very classic idea of what an experiment, data collection, and sort of the process of science, if you want to go as grand as that, looks like. And this is a process maybe where we have some alternatives that we're interested in, think A/B testing kind of language, and we trial those in the real world for a while and collect some data. We collect this data, we look at it, we fit a model maybe, and we decide, right, okay, cool, this is the understanding of the world that I've got to, this is what I think I should do going into the world in the future, these are the recommendations I should make to people, these are the rules that I should set up, and then we do that. And this kind of style of thinking comes from, I view it as coming from more traditional kinds of data analysis and experimentation, where really, you had one opportunity to go out into the world, and then you had to go to a boss somewhere and make a decision about something. You had to say, this is the product we're going to use now, this is the mode of operations that we're going to do. And in contexts like recommendation, and then increasingly kind of in modern contexts where we have a little bit more flexibility with things because of technology, that's a slightly outdated way to approach tasks where we have freedom to be a bit more flexible. And one of the big questions then about this kind of classic experimentation setup is, well, how long do we experiment for? If we're thinking of recommendations, how long do we just sort of randomly show people stuff so that we build a data set? Well, that kind of depends. It depends on how long we're going to use the thing for. There's some kind of trade-off there. If we're going to use it for a very long time and commit to it, we want to be very confident. We want to have collected a lot of data and be very certain. If we think that we're maybe going to have things that have got a very small difference between them, again, we need a lot of data to be very confident about which one is the best. So really, it kind of depends, and that's a bit of an issue with this framework. It's an issue that you have to build in some assumptions, make some decisions there as to, okay, how much data do I want before I make this commitment? If we move into a slightly more complicated setting, which the point of today is all about this, right? The idea of personalizing the products or the items that we show to different people. Maybe for one type of customer, the product that they would most like to see is different to others. And then if you're looking at that kind of approach, is the idea of just exploring and collecting data for a fixed period of time, is that even appropriate? If it were to be appropriate, if it was to just, right, I'm going to do this homogeneous data collection section, that hangs on the idea that all the customers are kind of equally represented within that. It hangs on the idea that for all types of customers, it's equally difficult to learn what the thing that they like is. Some of these customers, it might be blindingly obvious what they're interested in. You don't need to explore for as long. So this kind of motivates the idea of being more adaptive in our exploration and doing this kind of real-time experimentation where rather than just collect one big data set, analyze it and make a decision, in contexts like online recommendation, we don't really have to do that. We can incorporate the data as we get it, improve our decisions as we go, and also if data comes along later that contradicts what we believe our best decision is, we can go back and change it. And so this talk today is really going to look at this idea of rather than just do exploration at the start, incorporate this data collection and consciously data collecting throughout the process of kind of deploying a product, deploying a recommender model. So the aim, hopefully, is that we'll get to the point of understanding why it's necessary to do that and some kind of broad ideas of how that is realized in practice. So to motivate this, I'm now going to move away from explicitly thinking about recommender systems and introduce something called multi-armed bandits, which are a kind of toy problem in mathematics and statistics that have found application in this area. So I want you to imagine, and for some of you this may be more in your personality than others, but I want you to imagine that you go into a casino and you are presented with kind of a set of different slot machines. You are agnostic to the fact that these are all rigged and it's a hopeless exercise to be there, but you have like a bag of coins with you and you know that these different slot machines have got different chances of paying out money when you put your little tokens in. The challenge in front of you is to leave with as much money as possible. Convert these tokens into as much cash as you can. And you have no prior information on which of these is the most successful, which is the most likely to give you the most money. So you have to do some experimentation. So you might select this first one, put a coin in, and hey, it gives me some money out. You try the next one, and it doesn't give you anything, and you try the third one, and it doesn't give you anything. So you say to yourself, okay, I'll go back to this first one. Okay, it doesn't give me money every time, but I'll try it again because it's given me money before. And this is a logical way to approach this problem, right? You wouldn't just take the first thing that works and then stick with it forever, because it's one data point. Hopefully we kind of know that one data point is not something to make a decision on the basis of unless you're really stuck. So we start thinking, maybe this isn't so high, I'll do some more exploration, and I'll move along to this third one and start to see some more data. And eventually the idea is that you kind of repeat that process, and if you're approaching this kind of toy problem optimally, what we'd hope to see is that eventually we realize that, well, maybe this one is actually the one that has the highest on average chance that it pays out. This one is really bad, maybe it's 0, but we kind of get to a point where we realize it doesn't matter what it is, it's lower than the others, and that's all we need to know. We're going to stay away from that machine. And we'd hope that we get to a point where we've used the one that's most profitable more frequently than the others. So this was kind of a toy problem that was studied as far back as the 1930s, more so in the sort of 50s, 60s, 70s in mathematical literature, and in that way that mathematicians do, where it kind of has a vague application, but really it's not directly useful to anyone at the moment. And then the sort of 90s and the early noughties came along, and companies started becoming interested in making recommendations, in personalizing and tailoring and optimizing web content. And so if you think of kind of the early players in this were news sites, were search engines, and they maybe have various articles that they can show to people. And the idea is that different articles, if you show them to people or you show them in a particular order, they might click on them or they might not. And this was seen to be one of the first real kind of concrete, nice applications of this toy problem, and somewhere that people were able to take the thinking from that and apply it. So online recommendation brought these really neat applications for this multi-armed bandit problem. Because it was a setting where it was easy to switch between different actions. Maybe not immediately in those days, but certainly now. But you could show different content to different people quite easily. You would get more or less immediate feedback. You know, people click on it, the website can record that and say, great, cool, that worked, that didn't. And debatable, but hopefully it was quite a low stakes decision. Maybe increasingly, you know, the outcome of recommendations and those sorts of things, we could debate that for quite a while as to whether it's low stakes or not. But maybe back in the, you know, in the inception of these kind of ideas, whether it was, you know, you show someone's Wikipedia page before their IMDb page or something, if somebody's searching for an actress, like, I don't want to give too many particular examples because even those you could start to think of ways that they become insidious. But it brought lots of neat applications and things like recommending news articles, films, online shopping, and you know, kind of tailoring websites and ads. And what was really great for this community was that that meant that when this literature, the techniques for solving these problems developed into more kind of usable, got into the machine learning communities and the growth of this area really started, it meant that the recommendation was the kind of go-to application for these things. So that was great for recommender systems folks because it meant that, you know, they were kind of driving what the research area was and in the research directions were in this area. But of course, real recommendation problems are more complex than this toy example of I have 3 non-connected things with different success probabilities. Of course, in recommendation, we have massive and changing item sets, and it wouldn't do to treat them all as different. We, of course, exploit the interdependencies between these so that we can cope with the fact that there are heaps of them and exploit the information that's there. We might have additional constraints like capacity limitations. If we show everyone the same thing all the time, eventually that will sell out or become redundant, or news articles aren't relevant after a certain amount of time. And we also have the aspect, the theme of today of personalization. It's not the case that every time, we get these kind of repeated interactions with the items, we get different people come to a website and click or don't click on things, but we have different preferences to each other. So someone that likes one movie, they might have a different profile to someone that likes other ones. But as I said, these complexities and these different bespoke challenges of recommendations were really the ones that this community concerned with how to explore and learn parameters and learn optimal decisions had in their mindset. And despite the additional complexities of real recommendation problems, I do think there's a common problem at the core. The idea is basically to get to the point of optimizing, get to the point of choosing an action with the best chance of success. Compared to a statistical analysis in something like health or epidemiology, you could argue that there's less focus on inference, less focus on knowing exactly what the probability that someone is going to click on this thing is, and more focus practically on, I just want to know what the best one is. I want to know what is, we'd love to know both, but oftentimes from a business perspective, it's about getting the best outcome rather than understanding the specifics of why. So think of this as the kind of overarching goal, to choose the action with the best chance of success. And that might be really straightforward. In this setting where we just had these three simple alternatives, that is basically figure out which of three numbers is bigger. As simple an optimization problem as you can get, hopefully. Or it might be more complex. We might have this personalization aspect going on, we might have heaps of items, we might have things selling out and available at different times, and we might be wanting to maximize the probability that someone clicks on something on our site, given the particular thing we choose to show them, given who it is, what day it is, what time of the year it is. It might be this horribly complicated model that we build for this probability of them clicking on things. Have heaps of parameters, heaps of interconnecting parameters with different users, but the overall goal, the overall kind of philosophy is the same. We're still trying to find the best thing amongst this set. So I want to deliberately be agnostic about that when I start to speak about how to build exploration into this process of learning those optimal actions. And think of us as having kind of just a statistical model with some parameters that we don't know, whether those are just those three numbers that we're comparing or whether these are complicated regression parameters or parameters of some nasty, huge neural network. What we're interested in is the probability of a success given choosing particular things to show to people and particular covariates of that problem at that moment in time. So what I want to motivate now, go back with this example in mind, is to think about why this exploration idea is really important. So we're going to formalize the following setting a little bit more. We're in this setting where repeatedly someone comes along to a website, we have a set of things that we could show them, we weigh up our data that we've collected so far, assuming we have some, and decide what they're going to see, show them something which they either click on or don't click on. Maybe it's a little bit more complicated than that. Maybe they can click on a few things, browse the site for a while, but let's keep it simple for the purposes of this. And then that data goes back for the next time that someone else comes along, and maybe we've even got different things that we could show them, or slightly different things. And we iterate this process, with the idea being that as this process has been running for a while, as we've collected more and more data, we should be in a position at the end where we're hopefully showing people the right things a lot of the time. So I want to outline why two very extreme approaches to this problem will fail. The first being purely focusing on exploitation. So what I mean by exploitation is to behave very greedily and very only thinking of the very next customer that's coming along. So if you're only concerned with serving the person directly in front of you, the logical thing to do is show them the thing that you think they will like the most. So you will always focus on the kind of highest part of bar in your data set. You'll always show this person the thing that you think they are most likely to click on and most likely to be satisfied. This is great for this guy. He's thrilled. He's getting exactly what he wants. But for the overall model building, for your overall process of learning these optimal actions for future people, it means you're only getting data about one aspect of this system, potentially. You're only getting data about the thing that you already know and understand. But if you have a lot of uncertainty in your system elsewhere, you're not doing anything to reduce that. You're not doing anything to learn whether or not that is the best thing to do. So this approach is one that can be very variable, basically. It might get lucky. You might start with a really kind of good model. You might start with having a good guess as to people's preferences, reinforce that as you go, and great. Or you might get stuck. You might have something, an action that is really good for certain types of customers, but you immediately see a few bad data points and say, nah, not interested in that, they don't like that. And then you never go back to it because your model that you're always believing and never gets any more data to convince you otherwise doesn't say go there. It never will say, that's the best thing to do, try this. And you just don't know. You don't have the counterfactual to say that this is wrong. The opposite approach to this is one of pure exploration. So one that will just, when this type of customer comes along, they just cycle through the different alternatives, totally ignoring we've taken out this data analysis and optimization part. Always seeking to experiment, always seeking to use the thing that will get the most information for the model. And that builds the most accurate model. I've put an asterisk on it because it's accurate in terms of, in a certain sense, it might not be most accurate for knowing the optimum, but it will learn everything kind of equally, but it never capitalizes on it. And this one hopefully is an easier sell as to why that is not a good thing to do, because it never seeks to optimize, it just seeks to learn about the world. So what we really need is a balance of the two. We need something that learns about the world until it's confident enough to make good decisions, and then capitalizes on that information at some point. And that really comes down to how we do this data analysis and how we do this selection of decisions. So gently, from a statistical perspective, which some of you will be pleased to hear, I'm sure I won't go into too much statistical detail, this is ultimately a question of having enough data to tell the best option from others and enough to be confident enough about it for however long you're going to use it. So imagine we're back in this simple setting and we've collected some data from these two slot machines. And we've got to a point where this one has got a slightly lower return rate, more failures than successes, and this one's got a slightly higher. And maybe we have these graphs then that represent our belief about the different probabilities of this, these machines giving successful outcomes. And at this point, you know, that it shows that we think the blue's better, but we're not 100% sure about it. We're not entirely confident. But if we were only going to make a few more decisions in the future, maybe that's good enough. Maybe that's the point that we say, right, okay, I just want to get as much money now. There's no value in learning anything more. And you know, you have these kind of trade-offs in mind, this idea of how much more confident do I need to be. Later, once we've collected much more data, we're maybe in a position to bank on this information for thousands of goes of iterations of this process. Because at this point, the overlap between these two graphs now, once we've got a much richer data set, is very small. So how do we go about striking the balance? Well, I'm going to speak about two very general principles that are used to do this, that can be applied and are applied throughout a lot of the literature. So one of the ways to do it is this idea of optimism. So while my purely exploitative approach, the greedy guy, always did what it believed to be best, in terms of the probability of success, my optimistic approach values both the chance of being successful, but also the information that can be gained by an action. So instead of just maximizing the probability of someone clicking on it, we maximize a sum of a term that is the probability of clicking on this item, but also how uncertain we are about those. So why is that a sensible thing to do? So imagine we've got these two kind of belief distributions at the moment. One action that we know a lot about, we know roughly what it's going to give us, and one that we think is worse, but we're really not that sure. We're quite uncertain about how good it is at the moment. If for those two things I take like a high kind of optimistic view of this mean, I take this kind of probability of a click plus some measure of of how uncertain I am about it, I might get these kind of values. The blue one is this value here, and the pink one is this value here. And the idea of this optimistic thing is that for things that we don't understand well, it attaches a kind of inflated sense of the value of that until such a point that we start to understand it well. So what this approach would do then is say, okay, the blue looks good, I get it, the blue looks good, but the pink I really don't understand that well yet. And given that I'm going to, choose between these maybe for quite a while in the future, let's just try the pink and get a little bit more data. And then that same kind of principle, once you become more certain about the pink, once it starts to get a bit more peaked, will eventually move that back below the blue line, and it will start to pick the blue as the preferable of these two options. And what it will do is it won't let the pink get to the point where we have to have explored it as much as the blue one, because it will say, actually, you know what, that's enough now. Even with being optimistic and even with taking a kind of best view about this, I'm quite aware that this isn't working. Another approach is similar, and again, rather than just using the kind of purely the probability of a click, it just adds some random noise to this. And this can be positive or negative noise, but again, it is proportional to how much uncertainty we have in the data. So this one is definitely easier to explain with the graphs, but instead of using just the center of these two distributions, we add a bit of noise to it. We basically sample from the distribution of where we think this lies. And sometimes, a lot of the time in this situation, the blue one, if we add a little bit of noise to that, is going to give a larger value than the pink one. But sometimes, you'll get different values because we're being random here. We've added a little bit more positive. And eventually, at some point, because this pink one has a lot of uncertainty, because this randomness that we're adding has got higher variability, it will come round to using the pink action. But it won't do it very often because the blue one is quite clearly better than the pink one. But the idea of this adaptivity to the uncertainty in the data is that it will do it in a way that is appropriate automatically. It will, for things that are very, very bad, you will have to have a very, very extreme set of samples to query that thing. But if two things are very close to each other, then it will constantly be kind of switching between the two of them because the randomness will shuffle which one looks to be the best of the two. So I want to quickly conclude with not a very rigorous, but an example of where I've used this in my own research. Everything so far has really been summary of the literature, and to be honest, this is also quite high level, so it could equally be a number of different papers. But we've looked at this in the context of models of learning to recommend sets of items on a web page, a task that a lot of the people in this audience probably do in their bread and butter. So learning to decide which items to display on a furniture site here we're using as the toy example, deciding what position they should go in, so shuffling them around the site based on the idea that different positions might be more prominent, and looking to maximize the number of clicked items over time. So in this paper that I won't go into the full details of, we formulate a model where users look at these simultaneously and weigh items on the basis of how relevant they are to them, but how prominent they are as well. And if you know all the parameters of this model, if you know how attractive everything is to a particular user, if you know which positions are the most interesting ones and how much more interesting they are, the solution is really straightforward. You would just put the best content in the most prominent places, and it turns out not to be that surprising. So we can use an optimistic approach in this setting instead. And what that will do is match the best asterisk, come back to that content, to the most profitable positions, but where instead of best meaning purely most attractive to the user that's in front of us, best means this combination of attractiveness to the user, the probability that they'll click on it, and the uncertainty that we have about it. So a good action, a good item is one that either people we know will like, or one that we could stand to learn something about, something that if we put it in a prominent position, we're definitely going to get some kind of signal about it. It might be that the user hates it, but we'll get some information, and for future users, we'll be able to be more confident. So how do our approaches that we've spoken today perform on this problem? On the x-axis, I've got number of users, essentially, that we've shown combinations of things to, and on the y-axis, I've got a measure of how far that that set of actions is from optimality. This is called the regret, so it increases the more bad actions we make. Purely exploring, unsurprisingly, is terrible. It just goes up and up and up because it's not seeking to optimize for anyone. It just learns a lot about the world, but doesn't ever capitalize on it. Purely exploiting is very, very variable. So sometimes it works great. It gets some good data at the start, and it basically is almost perfect initially. And sometimes it's terrible because it does this thing of writing off good items, writing off good actions very early, and then just getting stuck in that and not getting data to tell itself that it's wrong. Something like an A/B test, where we do a fixed period of exploration and then commit to the best action, is a little bit like a combination of the two. It will look like the exploration approach while it's doing exploration, and then it will inherit this kind of exploitative. Maybe it wouldn't be quite as bad as that. I forget exactly how I've put this together, but it would. You see, it's got a more shallow gradient on average than the pure exploration, because it has got more information at the point that it starts to commit. But the Bandit, the optimistic approach, it manages to kind of capture the performance of both. It manages, by exploring and exploiting, to have a period where it grows more rapidly at the start and then start to plateau later on. It won't always be as good as the lucky version of the exploitative action, but it's more reliable. It's more assured because we know that it's taking into account the data in front of it and making sure to strike this balance, which from a business perspective is often more valuable than, you know, a marginal improvement in the average performance, because we're only going to do it once, and if it goes horribly, horribly wrong, that's not good. So in summary, I hope today that I've kind of got across to you this value of incorporating exploration continuously within this process of making recommendations. There are other reasons. I've not touched on the fact that parameters might change as time goes on, and we want to be able to respond to that as we go. We want to be able to deal with rare customers of strange types that come along that maybe wouldn't be expected to be in a small exploration site, but we wouldn't want to just keep exploring blindly until one of them comes along. We want the adaptivity to say, this is something new, I'm going to put my exploration hat back on. I don't know what an exploration hat is, but you know, we're going to be flexible in that regard. And how is it realized? Well, I hope I've given you a brief flavor of these kind of approaches that, crucially, the crux of them is that they're considering the uncertainty at every time they make a decision. So they're more computationally intensive, of course, because it's a more intelligent decision-making process, but they're smarter with how they use the data, and they're adaptive to this. And these techniques are used and can be implemented with a range of different techniques. I've presented very simple ideas, but I hope that you can take these ideas and think about them during today and how they can interact with the much more complicated stuff that I'm sure is going to follow after. So thank you very much for your attention.
Great. We have time for questions. Good. Many questions. Kim, you can start.
Thank you. Great
Hi.
talk.
Thank you.
Kim from Shopify. So you talk about A/B tests first.
Yeah.
And you say the problem with them is that we have to wait because we don't have confidence. And then the solution is to do multi-arm bandits where you just shift things in and out. But how often do you think that you take a good solution and you shift it out because it needs time to actually, become accustomed to the system?
Yeah, totally. So that is, you know, when I had this kind of exploitative performance. So if I go back to here, I've got this thing that can, sometimes it's terrible, sometimes it's great. And the situation you describe, and for anyone that couldn't hear it at the back because of the way the room's set out, the question is, do these risk taking these optimistic, these bandit approaches, do they risk taking something that is good, it's great, it works, and not using it because it wants to gain more data? Is that essentially what?
But basically what you say, that we take something where we wait for confidence,
Yeah.
and then you shift it in something else where we don't wait for confidence, and then we just push it out if it doesn't work in the beginning. And that's kind of also the problem with the A/B testing, because you have to wait for confidence.
Yeah, so the idea is that it's more adaptive than A/B testing. So an A/B test, if you don't know how different these two things are in the outset, you have to kind of plan as if they're quite similar to each other, and you want a lot of evidence to tell the difference between the two. The idea of the Bandit approach is that if, as time is going on, it's abundantly clear very early that they're quite different to each other, and you didn't have to spend all the experimental load that you would spend in an A/B test, it will start behaving like they're very different to each other much quicker. It will say, no, I can rule that one out. I don't need to waste time exploring it. And equally, if at the end of what would have been your exploration window for an A/B test, you still aren't sure, that algorithm is kind of going to automatically continue doing that. That's the way that it's built. And the other thing that's really nice is once you get to stuff that's much more complicated, where we're not just looking at two alternatives, we're looking at a spectrum of alternatives or a combinatorially large set of alternatives, how big your A/B test should be, how you compare the different parameters within it becomes very complicated to set up initially. But these ideas they start to become more clearly the appropriate ones, I think, because they're considering the model and the uncertainty as a whole, and they're always kind of making the trade-off that essentially we have to make blindly beforehand by guessing how long to run exploration in the A/B test for. It is subtle. It's a subtle point, and it's one that I could probably talk for a long time about, but that's the gist of it.
Yeah. Multi-arm bandits.
Great.
So
Yeah.
One last comment, and then this summer, this autumn at Rexus, there was a paper saying that we have to be more pessimistic. Yeah. Which is basically the contrary of what you're saying, because he was saying that we would actually throw away a lot of good examples because we would be too optimistic. Yeah. So it's weird. The optimism and pessimism, these are kind of conflicting words, because in some ways what we're really doing is being pessimistic. We're saying I'm not going to rule anything that looks bad out until I'm really sure it's bad. And compared to the randomized approaches, they have a bit more flexibility. They can be a bit quicker to learn, actually, because the optimistic ones want to be quite certain. They're not the extreme of this green line, but they don't want to rule anything out until you have good statistical evidence for it. And depending on your stakes, depends on whether that's appropriate for you. Thank you.
Time for one more question?
Yeah, Ravi from Canada.
Hi.
What did you mean by uncertainty? Is it the marginal probability for like non-convergence?
Yeah, that could be one interpretation of it. So in the very, very simple setting where we've just got these three alternatives, we'll have a point estimate of what we think is the most likely value of this probability of the machine giving you a coin or whatever, and then we'll have some sense of how sure we are of it. And so yeah, this is kind of, if you want to be Bayesian about it, it's your belief distribution. If you want to be frequentist statistician about it, it's your confidence interval. It's an upper limit of that is what you're using. If you've got a much more complicated model, different models will have different interpretations of those. You might have to be quite heuristic about it if it's something like a neural net or something. But if it's, from my world, like a sort of regression or a Bayesian model, those are kind of built in quite nicely. So there's a range of tools in this area for different ways of quantifying uncertainty and using it within these algorithms. It's an important point, though.
Are you incorporating like some weights when it comes to like parts of website, for instance, or whatever? Like, are you using that like to make it not only like Bayes marginal, like this is how you play with it?
Sort of analogous to that, yeah. It's not that particular paper isn't a Bayesian analysis, but it's using frequentist confidence intervals and taking kind of a strong assumption about the choice model that the users are using, and then letting the kind of uncertainty that implies. I can chat about it more offline if you're interested, but yeah, it's yeah.
It's really interesting to like a hyperparameter.
Yeah.
Thank you.
Good.
Great.
Thanks a lot, James.
Thank you.
Right, next off is Christoph Trattner, and you will talk about online food recommendation, a complex problem.
Yes, so thank you very much, Simen, for the introduction. I hope my voice is loud enough. If not, then just tell me, because I was hiking on the weekend and I have a little bit of a cold. Yeah. So let's have a look what I have for you today. I am doing a lot of research on a lot of different things. And one of the things I like to do is research on food recommendations and media. And in this context, I was also founding with my colleagues a center called Media Futures. So this is one hand I have on at the moment. And I lead also that center. And then on the other hand side, I do this food research. Yeah? Before coming to Oslo, I was thinking of what shall I present. And since I saw so many cameras here, I thought like, okay, maybe let's go with the food research, yeah, because we have so many interesting things for you to show in the future in the context of media. And let's focus on that. And my mission is to improve diets, so I do both media diets and food diets. And today you hear the food part of it. So good, let's have a look what I want to tell you about today. So I want to tell you about what is the motivation of my research. So what are the factors that influence the food choice of people? How can we alter food choices? So we're also organizing this year at ACM Rexis conference a workshop on how we can use recommender systems to change people's behavior. So here you hear a little bit about how we can do that. And then I also tell you a little bit about the future of how we are doing research in a research group. Now, what is the problem we would like to solve? Yeah? So I think all of you know that food is the most important thing or when it comes to staying healthy, apart from doing exercise, yeah. And also there are some, reports showing us that from the World Health Organization. We know that food affects how we develop, for example, heart strokes in the future, type 2 diabetes and stuff like that. So we have to eat healthy to stay also healthy, right? And if you look into statistics, yeah, then they typically look like that at the moment. So BMI is going up, yeah, and everything is getting red. So we have to do something about that. Yeah? And how can we do that? Well, we could, for example, use recommender technology to help people to implement more healthy diet. Yeah? And if you also look into how people do food interactions these days, so then they are most of the time actually online and not so much offline anymore. So especially it was peaking during the COVID pandemic. People went online and still over many in Norway, and then we do this online these days. Yeah. But interestingly, if we look into literature, we discovered that there's a lot of people doing research still on grocery markets, how to persuade people to take the healthy choices there. But not so much research is done on how we can persuade people to do the healthier choices, choosing in the online world. And this is actually what I want to talk today about. I want to talk about this online world and factors that influence those food choices and how we can use those factors, those biases, those influences to make people choose more healthily. Yeah? So if you think about like a user, you're going online and then you have maybe a time constraint, you have to cook something in a very short period of time. You think about, okay, I'm in a certain location, so then certain grocery is available to me. You're in a social context, you're getting peer pressure by your husband or by your kids, telling you what to cook. And then there's also certain culture in your family that affects you. And there are many more factors, obviously, that affect us, how we take those decisions in the end. Price and so on. And when we look in the online world, so this is a typical recipe website, for example, kochbar.de, that is how I started my research back in the days. Then you have a recipe, for example, that gives you a picture, an impression on how things look like. There's a 5-star rating, for example, or any kind of rating that gives you an impression how people perceive that recipe. There are ingredients, there are like explanations how to cook that, and many more factors. And there's a person maybe that is the creator of that recipe that also has an influence of that food choice, right? So in order to understand how people are influenced by all those factors that we see, and there are many more of those than you see here in kochbar.de. If you go to Chef Koch or any kind of other website, meni.com, or Rema 1000 or whatever, then those are factors that you could see. And then you could think about yourself, what are actually, how we're influenced by that. Yeah? And I started back in 2014 with an analysis of kochbar.de, where I wanted to understand the factor of time. Yeah? So people choosing recipes, because back in the days, these time-based recommender systems were quite hot, you know. I know that you guys still are very interested in the news domain, in the factor of time and how it decays, you know, and so on. So we are still talking with you a lot about those things which we did back in the days in 2014. And actually, when you look into how people choose recipes over time, so between 2010 and 2014 in the recipe platform, that you see then trends. Yeah? You see like people are more interested in high protein recipes in the summer, less carbohydrate proteins in the summer, but high protein, high carb recipes, for example, in the winter, right? So then you can use those trends, for example, to recommend people more healthy choices in the winter than in the summer. Yeah? Visual appeal is also something that people have been exploring in the offline world. Yeah? We also try to understand those visual appeals in the online world. We were running experiments showing people A/B, you know, which of the two would you choose? And you can extract features from images now these days. Back in the days that were like brightness, sharpness, contrast, and so on. Yeah. Now you have all those fancy deep learning architectures. We also played around with VGG16, ResNet, and stuff like that, and found out that we could predict the food choices of people. I show you then later how we used that also to alter then food choices. We also looked into innovations. Yeah, so we are an innovation center. Then you also have to look into innovation. That is a research we have done back in the days in 2015. Here you see actually how recipes have been, so over 400 days, and how recipes have been published by people and how they have been consumed. So you see the number of users, the number of recipes, the number of ingredients that have been used, and stuff like that. And what you see from that graph is actually quite interesting. So while the number of ingredients goes steady, of course, because there has to be some saturation, yeah, the combination, how people use those ingredients, yeah, is still increasing over time. So that means people try to still innovate on the number of subset, which is fixed with making more innovative recipes. And then we also try to use those factors to predict popularity of, for example, recipes on allrecipes.com. So you can also use these kind of models to predict any kind of popularity. So that's like standard feature extraction. So what we did here is we used recipe complexity, healthiness, innovation, nutrition, presentation, season, and user activity as factors. In the plot, you see the variable importance, and then you see the model accuracy. We used random forest in that purpose. So we could predict whether or not a recipe would become popular within 30 days by accuracy of 70%. And then you see that the green stuff over there is recipe innovation. So people, for example, in allrecipes.com, they go all for their innovative recipes. They all want to get like those recipes that use a special combination of ingredients, for example, in the recipes. Yeah? You can also do the same in other countries, like in kochbar.de is a German website, so the US people are more on innovation. In Kochbar, so it's a similar recipe website to allrecipes.com, we could predict to 90% of accuracy whether a recipe would become popular, and that is based mainly due to user activity and context. Yeah, so the more you interact with your peers, the more active you are, the more likely your recipe will become popular. You know, and then after understanding those trends and factors, you can also then think about how you can use that for altering food choices, of course, right? So let's talk a little bit about more about that, and let's talk about how current standard recommender system methods perform. So we did analysis of that in the past. We're running experiments where we were using as input user interactions, ratings, on recipes and allrecipes.com. We're running standard algorithms such as PPR, most popular user KNN, item KNN methods and stuff like that. Yeah? And then discovered that those food recommender systems typically produce unhealthy lists. Yeah? So, okay, now how can we improve those things? So when you look into those details a little bit more as an engineer, so I suppose that many of you are engineers or also at least users of those recipe websites, then you discover you can either look into algorithms as an engineer or interfaces, not so much at the users and the items because they're typically provided by the platform, yeah. But what we can do, as engineers, we can manipulate the interface and the algorithms, yes, yeah. So what we did, of course, is here you see results on influencing the algorithm. We did re-ranking, and here you see the results from the previous experiments on the top. And then you see the results of the new algorithm at the bottom. You see we get a little bit more green, means we get better and more healthy recommendations. Yeah? Another experiment what we were running was influencing the interface. Yes, and I'm almost coming now to the end. So here we tried to manipulate the items in a sense how they were presented. And you see here similar items, so top and bottom row are similar. So for example, to the right-hand side, you see a soup, yeah? And you can have the choice of presenting an ugly picture to the person or a nice picture to the person, right? And of course, what we know is that people typically go for the unhealthy food choices. Yeah, this we know, yeah, because that's how our brain works. We want to have high calories and stuff like that, yeah? But if I show you an ugly picture, yeah, then I most likely get you not to choose it, right? So what we did is we showed people ugly pictures for the unhealthy recipes and nice pictures for the health recipes. And what we could do is we could, predict those choices then by 65% accuracy. We also did similar things then in the search prototype later on with Alain. Maybe he talks about that in his talk also, and things like that. Now, what's the future? 30 seconds left, yeah. What we are currently working on is many things, but there's a range of things that are interesting for us. Mostly we're interested in the interplay between algorithms and interface, to be honest, because this I think is lacking in the research we're doing. We have in Rexis, we have the algorithm track, and then we have the interface track, but nobody's doing something in between, so I find that strange. So I think like we have to do something about that, yeah. And there will be a very smart person then coming. He's one of my PhD students, Ayoub. He will tell you then more about what we actually do. Yeah? So with that, I thank you very much.
Thank you. We have time for a question.
For one question.
One question. Any,
I have a quick question.
Yeah.
Like for some companies, maybe some foods are more, like the bad foods are more expensive and therefore more profitable. How do you manage the business side and the health side?
Yeah, that's also what we are currently investigating actually with some of our stakeholders. So because I mean the cost aspect in home is quite important, of course, yeah, and with the rising prices, this is actually something we have to take more seriously as we did it in the past. So food choices are, a multi-objective optimization problem, and in that aspect, you also, of course, have to optimize for the price. And then, you have to think about like how much you can push it. So there are models and experiments I can show you that show that price, of course, is an important factor, but you can push quite hard actually to get people to still pay a high price, yeah, by getting just a better food choice, meaning in terms of taste and how it looks. So that works quite well, yeah.
Good. I think that's all.
Okay. Yes.
Okay. Hello everyone. So I'm Ayoub and I'm a PhD student at Media Futures, working with Christoph and Alain Starke. So I'm going to talk about our first experiments in which we want to bridge algorithms and interfaces. And this experiment, we call it Nudging Towards Health, examining the merits of nutrition labels and personalization in the recipe recommender system. So I would like first to introduce you digital nudges. So digital nudges can be defined as the use of user interface design elements to guide people's choice or influence user input in online decision environment. So as Christoph mentioned, the motivation of doing this research, first, online recipes are unhealthy, and also algorithms recommend following the principle of bias in and bias out, which is BIBO. So algorithms learn from unhealthy recipes, so they will recommend what is unhealthy for people. And there is another motivation, which is lack of nutrition knowledge. And to show that, for example, let's imagine that you want to prepare a recipe and you went to allrecipe.com and you are looking and you found this recipe. And then you want to know the nutritional information about that recipe. And suddenly, that's what you see. You see a list of information that not all people know how to, let's say, how to evaluate the healthiness of this recipe based on this big list. And then what we propose to, let's say, to mitigate this problem is to build a nudge on top of a personalized list. And this, we can call it maintain personalization, but also include cognitive digital nudges, which is food nutrition labels. And why we choose those labels? Mainly because they capture consumer attention, and then they are easier to process, and also they influence consumer decision making. And the labels that are, let's say, that are help us to achieve those three factors are multiple traffic light that present a summary of what a recipe, how we can evaluate a recipe based on those colors in terms of health. And the second label is Nutri-Score that gives an overview of the healthiness of a given recipe. And to do this research, we formulated 3 research questions. The first one is, to what extent our proposition can lead to a healthy choices? And the second one, how can people evaluate our systems based on choice satisfaction and choice difficulty? And the last one, what are the factors, system factors, and also user factors that will tell us how the system can predict or leads people to choose more healthy options. And the methodology to do this research mainly is offline evaluation, and then we did a user-centric evaluation. For the offline evaluation, we choose all the recipe dataset, and then we evaluate or we implemented several algorithms. As you can see here, we choose basically based algorithms such as baseline, co-clustering, k-ning, and so on and so forth. But the best performing algorithms in terms of accuracy was singular value decomposition based on RMS-E and mean absolute square error. And then for the user experiment, we had three conditions. The first one is baseline condition, and the second one is Nutri-Score, in which we present a list of personalized recipes, and on top of those personalized, we annotate recipes with the label, with corresponding label. And the last one is multiple traffic light system as well. So to answer the first research question, so we did some analysis, and we found that basically what is surprising is that the random algorithms leads to more healthy choices, but our choice of let's say personalized algorithm leads to slightly low healthiness of choice, and that we can say that using labels leads to slightly more healthy choices, but only if the content is not personalized. So randomness leads to more healthiness. So for the second research question, in which we want to see how people interact with the system in terms of choice difficulty. This time, personalization helps a little bit and leads to low level of choice difficulty. So the people found which when they are interacting with the system that is personalized, it makes them make choice easily. And for the choice satisfaction, so it was a little bit hard for those labels to lead people to get satisfied with their system. So here we found that there is no significant difference between randomness and also between personalization. So we can say choice satisfaction was not significantly affected by personalization. And for the last research question, in which we build a linear regression and we want to see which factors are affecting healthiness of choice, those factors are system factors, in which we evaluate personalization versus randomness, and user factors, in which we evaluate, let's say, 18 goals, education, and I mean we integrate in that linear regression a lot of factors. And we found that personalization leads to unhealthy recipe choices. Users with 1 or more 18 goals likely to make healthier choices. So people, if they are entering the system and they have a purpose that, for example, they want to eat recipes with, let's say, less salt, they go to look for that recipe exactly. And the last one is how choice difficulty related to health depends on users' goals. So also choice difficulty affected by if you have a goal or not. So the main takeaways from this research, we can say that the influence of labels on the healthiness of recipe choice depends on the content is personalized or not. So personalization plays a role, even it leads to, let's say, to unhealthy choices. The second one is that when recipes are personalized and labeled, choice difficulty is reduced. So personalization without labels basically backfire. And the last one, the effectiveness of cognitive digital nudges depends on the use of personalization and user goals. So to mitigate this problem, so we introduced Boston, which is mainly helping people to understand what is the meaning of those labels. So before people making choice, we support them to understand the labels, because some people, they don't interact with those labels in real time. And for the results of this paper, so you can scan this code. And currently, we are working on bridging the gap between algorithm side, user knowledge, and user experiments. And we want to see whether or not, if people have knowledge in terms of nutrition, their experience will be, let's say, they will be satisfied, they will not find a difficulty, and then the system requires less effort for people. And the result of this research can be found in RIXIS in Singapore this year. Hopefully. Yeah, and yeah, that's it. Thank you very much.
Anyone else? Thank you. No? Okay, give me a go.
I'm sorry.
Yeah, no.
Interesting talk.
Thank you.
So the SVD,
Yeah.
when you use personalization, it's worse
Yeah.
health-wise. Isn't that like the popularity bias? Because you say that unhealthy food is always the most popular products.
Yeah, exactly. So it's kind of, you answered the question. So it's the popularity, the most popular recipes out in the internet are unhealthy ones. And then once those algorithms, teach themselves on those recipes, so they lead to produce what is unhealthy. And also, people, when they are interacting with those systems, so they look for personalization. So they give what they like, and the system is exactly mimicking that. So it will produce what you give them. So it's like also people, they are expressing unhealthy preferences when they are interacting with the system, and that's kind of why, to mitigate that problem, is to use those labels to support them making choices. So, and that's why, let's say, I think randomization leads to more healthy choices, because it gives, diverse recommendations.
Yeah, so like as was told, my name is Bjørnar Vassøy. I'm a PhD student affiliated with NTNU and the Norwegian Research Center for AI Innovation, Norway. Yeah, and I'm going to talk a bit about consumer-side fairness in recommender systems. So I will give you some highlights, I would say, because I don't have a lot of time. So without further ado. Use a mic? Okay, how? This works? Yeah. You can just try to stay it there. Okay, how's this? Good? Nope.
It's not good?
Okay. Kan du holde? How about now? A bit better?
Yes.
Yeah. Okay. Let's try that. So yeah, my motivation for doing this topic is that me and my supervisor wrote a literature review about this topic. We did it systematically, so we did go through like every single article we could find on the matter. But in particular, we looked at only articles that proposed an actual recommender system that did some fairness stuff. And also only consumer side fairness. So our model, a lot of these articles would have statements like, our model improves fairness, but there's no single definition of fairness to rule them all, unfortunately. We, in our research, with about like 40 papers or so, or more, we found over 30 different metrics. So what is the definition of fairness? And one of our main objectives became finding some common ground, like what are some high-level conceptual definitions of fairness that many can agree upon. So yeah, I will, in our paper and also in this talk, I will present two main ideas. One of them was the one I just mentioned, so can we categorize different fairness definitions in some high-level classes, if you will? And also second question, like, how has fairness been incorporated in different models? Yeah. So first, I will skip through like the 3 main high-level definitions we landed upon. But then I will explain them a bit further in a bit complicated graph that I will do piece by piece. So we decided on recommendation parity, utility-based fairness, and neutral representation. So I'm going to present you with a scenario here. We have a recommendation scenario. We have 2 different user groups that might be young and senior or male and female. They were represented by red and blue. Blue has a high preference for something. Red has a low preference for the same things. So a normal recommender system that has no fairness adjustments may produce something like this. For instance, if the blue class is dominating the dataset, it performs better for the blue class and slightly worse for the red one. And we also have a view below this where you look at the representation space, so what kind of information is encoded. And here you can see that the different users of the different classes can be easily separated. That is, the model encodes some information about the sensitive attributes. So first, for the recommendation parity. Models that optimize for this would idealize something like this. The distribution of recommendations given to the different user groups overlap. So this type of fairness definitions is typically pursued by, an example could be like a career recommendations where you don't want to, that nurse, the occupation of nurse is more recommended to women than to men, for instance. So yeah, that could be an application for this kind of fairness. On the other hand, utility-based fairness, you can see straight away that the ideal situation is very different. And in this case, it has sort of balanced out the utility, so now it performs equally well and equally bad for both classes. An application for this, for instance, could be like a movie streaming service, for instance, where the majority of the users are young, and it performs bad for senior users, but you want to lift up the performance for the senior users, despite the fact that that might destroy some of the performance for the majority users. And the final fairness classification we added upon, that we called neutral representation. They don't really care about the actual outputted recommendations. They just want to make sure that the model itself does not encode any information about the user-sensitive attributes. So in this case, in the representation space, we can see that you no longer can separate them easily. So the model doesn't know inherently if you're male, female, or young and senior, or yeah, whatever. But yeah, unfortunately, this is the real world. So these 3 main concepts only covers like 80 to 90% of the available papers. The remaining part have designed their own exotic and weird definitions of fairness that can't really be classified. But I won't go into details about those. So yeah. For our second question, I want to look a bit at how fairness has been incorporated in different models. And we use some familiar concepts in both fairness literature and also in general, really, where we have the high-level taxonomy classes of pre-processing, in-processing, and post-processing. These are pretty self-explanatory. So pre-processing methods, they take place before the model is trained or fitted. So that's typically data augmentation. In-processing models make changes, or methods make changes to actual models. And post-processing models, they don't do any changes with the models or the input data. They just change the output of an existing model. And yeah, in our case, for the consumer-side fairness of recommendation, we didn't really find any subclasses that we wanted to divide the research into for the pre-processing and post-processing. However, for the in-processing, we found 4 different main classes, if you will. I will give some examples from all of them, but I won't go that deep into detail, or not all of them, some of them. Yeah, so our first example is from Slocum et al. I'm probably mispronouncing the name. But they propose a pre-processing method where they have a lot of user interaction histories. And they want to make sure that they want to make sure that the users you can't tell what gender the user has based on the input data, essentially. And very simplified, they do this by removing items that are indicative of the user's own gender and adding some random items that are indicative of other genders. So that's one method that has been applied. The in-processing category of loss enhancement we defined is very simple, and it's very adaptable, and thus has been applied a lot. In this method, you simply add different loss terms to encourage your definitions of fairness. So you have the base recommendation loss, and you add some measure of discrimination or unfairness, and you penalize that in the optimization. An example that uses this and another term that we call adversarial. I won't go into detail in this complex graph, but in essential, these guys designed a news recommender system. And they trained two different user embeddings, one for predicting sensitive attributes of the user, and another one that is penalized for doing so. And then they also add like an additional loss term that wants these two embeddings to be orthogonal in the embedding space. In the end, they only use the bias-free user embedding to make the actual recommendations. And finally, we have a probabilistic approach, which uses probabilistic theory to model the influence of sensitive attributes into one variable. And then this variable is omitted during inference, essentially. Yeah, I don't have time to go through these tables, but these are essentially some of our findings and categorizations through taxonomies of the different papers we covered. And very briefly, this is the final slide. We have some recommendations based on what we researched. And that is, there is a need for consolidating fairness definitions. One problem with that everyone is saying we improved fairness without specifying what fairness is that it's difficult to tell which models can be compared. And yeah, do they even compete on the same arena or the same common ground? Furthermore, while some metrics, there has to be more than one metric, obviously, for even different types of fairness definitions. There shouldn't be 30. That's a bit too many. And finally, it would be nice to have some data sets that have greater ethical ramifications than movie recommendation, because unfairness in movie recommendations is not as impactful as in career recommendations, for instance. Yeah, that was it.
Great.
Any questions?
Setting up, are there any questions? I think one question for Bjørnar. Yes, Anastasia.
Hi, Anastasia, University of Media Futures. I'm working on popularity bias myself, so it's kind of connected with fairness issues.
Yeah.
Have you looked into which domains are specifically consider fairness more than the others?
No, like,
I think the question is which are more critical, to fairness questions.
Yeah, no, not really. We focused on the available literature, and like I said, most of them focus on the data set that are out there and that do have sensitive attributes, which is essentially movie lengths, a couple of others. So unfortunately, I can't really say that much more about that topic, but I would very much like to have some more relevant data sets, obviously.
Likewise.
Yeah.
Have you also observed the same trade-off between accuracy and fairness?
Yeah. There are usually some trade, like you have to sacrifice some accuracy is my general impression. There are some that claim that they can do it without sacrificing anything, but those are the papers that I doubt the validity of usually.
Thank you.
Yeah, thank you very much, Anastasia. Last question, is that a published study already, or can we
No, it's under review.
Okay, good. Then thank you so much, Bjørnar. All right, now we have Alain here, and he will talk about understanding
fairness metrics. So, thank you. My name is Alain, and I'll be talking about understanding fairness metrics. And I actually didn't know how good of a fit after the previous talk this would be, so now I'm really happy to take over Bjørnar here. But so I'll be talking about understanding fairness metrics, specifically how does the general public understand fairness. And this is work that was conducted by one of my former thesis students, Veronica, who did an awesome job. We've also submitted this for a conference, so this is under review right now. We'll see where it ends up. So the question I'll try and answer, I'll talk about, is whether we understand fairness. And to give you a bit of a background to this fairness thing, a few years ago, there was a lot of media debate about the Compass algorithm. A company called North Point Suite, now called Equivant, released this, or they produced this Compass software, which is used by parts of the American government as a algorithm to assess potential recidivism risk. So what it does is it provides a personalized reoffense score for criminals. So based on previous histories of what criminals have done, it sort of does this prediction of future crime. Sounds awesome, right? And ProPublica then, which is a news outlet, they wrote this lengthy and detailed criticism about the algorithm, saying, you know what, not too fair, this thing, right? So given that, all of this news and media stuff, we want to sort of understand how we understand, or whether we do understand fairness, like whether we take the stakeholder perspectives, all of the stakeholder perspectives into account, whether we look at like value alignment, what is it that we actually mean by fairness and so on. And also, you know, fairness is one thing, there's also accuracy, right? So we need to be looking at accuracy when looking at fairness. And, you know, having read this ProPublica report and the things from Equivant and a lot of like the other research and non-research analyses done on this, the general sort of consensus is that, you know, both of these reports are correct, right? Both of these prove or disprove that Compass is fair and accurate. It's just about having different definitions of fairness and accuracy, what Bjørnar was talking about, right? So, I mean, they're both correct in their sort of context. And Jonas, a couple of years after this, made an awesome analysis of this, specifically looking at the ProPublica reports, the Compass details and so on, and found that there is this disagreement about the appropriate definition of fairness. And that's that's the main problem, right? So Equivant did this thing that they claim is super fair and accurate. ProPublica made a really good claim saying, hey, you guys, you're not fair, you're not accurate, because we have different perspectives, values, and stakeholder alignments, right? And then Jonas continues saying that in computer science, in CS literature, and I'm assuming most of us here are from computer science, there's more than 20 different notions on fairness. Bjørnar just said there were more than 30, right? So there's a whole lot of definitions of fairness. And when we're talking about fairness, it's sort of really difficult to understand what we're talking about and in what context and what we mean by fairness. It's sort of this vague fluffy thing, right? So we tried to figure out whether the general public has some form of understanding of fairness and whether there is an agreement or understanding on fairness. And we tried to find this out through a user study. So quite sort of trivial, simple setup. We have this scenario where we're saying there's a hospital. It's using a decision support system to identify whether a patient requires attention or not. And the system then is used with two separate groups of patients. No different or different, doesn't really matter. There's just two different groups of patients. They both get to sort of experience this system. And there's two different settings. And what we're trying to compare is 4 different fairness metrics. I mean, Jonas and Bjørnar just said, there's 20, 30, whatever. We're focusing on 4 definitions of fairness, specifically on demographic parity, equal accuracy, equalized odds, and positive predictive value. And this is sort of like the presentation we gave to our study participants. We gave them like a description of this is the scenario, hospital, 2 groups of patients, and these are the sort of metrics that we're looking at. We gave them the description and like the caveats of these metrics. So like while they might be equally divided between groups, so like while it might divide attention equally between groups, so like demographic parity, it will do so regardless of group size. So, independent of the group size being 10 or 100, the same absolute number of users will get attention if demographic parity is used as a fairness metric. And so on, right? And we gave them 2 questions. Question 1 was, which of these metrics is most fair in a critical scenario? And a critical scenario being like if there's a risk of the patient dying if attention is not given to the patient, right? And the other question was, which of these is most fair in a non-critical scenario? Where there's no risk of dying, there's no risk of, some debilitating thing. It's just like you're in pain, you've broken a foot or something. So it's not super critical. You still would want to get the attention, but it's, you can wait a couple hours. And doing like a pre-study, we also figured out that we should add a 5th sort of option to give study participants the option to say, hey, I don't get it, sorry. I don't follow. So we added like a 5th option saying, not applicable, we don't get it. And we had like 130 something participants. So just like a, basic overview, question 1, which of these is most fair in a critical scenario? And there seems to be sort of like not a majority consensus, but at least some form of consensus that in the critical scenario, equalized odds is what like the largest group could agree on being the most fair. Okay, so C, equalized odds, equal odds of receiving attention in both groups, sensitive to group size. All right? And in the non-critical scenario, things changed. Instead, equal accuracy seems to be what's regarded as the most sort of fair metric to use. So 35% agreed that, hey, equal accuracy. All right. So in both of these, scenarios, we find that there's like a big group of people that agree. But, and there's always a but when we're talking about evaluation and recommendation and so on, like if we would remove the sort of the most common metric that they agree on, we find that in both the critical and the non-critical scenario, 2/3 of the respondents don't agree, right? So 66 and 65% do not agree with the top choice for fairness. And there's also like a significant chunk that just don't get it. They're like, hey, I'm sorry. No, right? So it's like this is sort of telling us that, do we understand fairness? Well, no, not really. This is sort of this reminds of that fairness is just another thing that we can measure. And it's similar to like when we're measuring accuracy, right? There are so many different metrics to choose and pick, and it's really important to pick wisely. And this sort of reminds me, at least, of the discussion we've been having in general evaluation, like when we're talking about accuracy, whether it's CTR or precision or RMSE. We can't agree on what the best metric is for accuracy. Of course, we're not going to agree what the best metric for fairness is, because this is like super contextual. It has so many different factors that are sort of outside of the algorithm. It's really tricky, right? So regardless of whether we're talking about accuracy-based or non-accuracy-based evaluation, so fairness or accuracy, it's going to be tricky. People aren't going to agree on like, hey, this is the main definition that we have. And in the last talk, Bjørnar said, we need to consolidate into like what fairness is. And like this is the same thing we've been talking about in evaluation. We need to consolidate and figure out what the best way to evaluate is. And we've not done that, and we're not going to do that. And the same thing, I think, at least applies to fairness. Like we're going to be talking about this, and it's really important that we talk about it. But we're not going to, have this one definition that we all agree on. And with that, I open up for questions.
So who was first? I didn't spot, but maybe you. Yeah. Thanks. Alexander from Curated. My question, it's actually kind of also for Bjørnar. It was for Bjørnar before you started. And I'm glad it was delayed. Speaking of sort of number of metrics on fairness, it seemed to me that, 30 is too many. Maybe the question is not about how many you need to choose from. Like you say, you have now 4 different metrics for one specific scenario. But out in the world, there are a gazillion different scenarios to design from. And choosing what you mean by fair is mainly a policy decision, right? From non-technical people. So my question is, does it make more sense to look at what procedures can we put in place so that we can translate a politician, manager, sort of oral discussion about what is fair into something mathematical, rather than having a set of mathematical formula to choose from without necessarily understanding what they mean from one set.
So like being a computer scientist, I hate to say this, but like I don't think we can have a mathematical formulation about this. Like we need to look at the policies, the governance documents. I mean, the EU has released a document on like AI fairness. The Chinese government has released a policy on AI fairness. Like each and every government organization, government, NGO, you name it, they have their sort of policies on how we should reason and think about this, and that's what we need to look at. We can't say, hey, green 3, that's what we're doing, right? That we can't have that type of definition. It's really contextual, situation aware, based on the users, stakeholders, and so on.
Thank you so much, Twan, and then
Twan Bogers, IT University of Copenhagen. So your category of, sorry, I don't get it, right? Maybe I missed it, but how are these people, did they not understand the definitions, or did they not know which one to pick in a particular situation? Because depending on who you are, you might have to explain the definitions in a different way.
So we did before we did this 130-person study, we did a sort of a pre-study, right? And in those 10, 12, I can't recall the number, it was like either they just couldn't grasp the context of like, what does fairness mean here? Or they didn't understand like the definitions, because it was like, how does this affect like they couldn't sort of link the metrics to what they would actually experience. So it's various different understandings or misunderstandings.
Okay, so now we make a transition. Simen, you come in front, and you take the last question, which is very short. Okay? Yeah.
Fairness is really about maybe not being treated unfair. Is there kind of a discussion? I was in the seminar yesterday where they talked about that trust and distrust are not opposites. So maybe instead
Yes, and this is, I mean, if there are 30 different definitions of fairness, they're not going to be polar opposites of each other, right? They just capture different stakeholder perspectives or different values in what we mean as fair in that specific context. So I think, I mean, we can talk about fairness, unfairness, it would be something that is, let's see, something that is, there's not necessarily something that is a polar opposite of fair.
No, I think it's not like that unfairness might not be
right, so hello everyone. I realized I didn't introduce myself many times I spoke, so this is a good opportunity. So my name is Simen. I work in Schibsted now, but I used to work for this subsidiary Finn.no that you might have heard of if you're from Norway, with doing recommender systems. So I did this for a long time, and this work is sort of joint work with the work I did in Finn, but also I have a everlasting PhD. Yeah, I see you're laughing, Arnoldo. But it's 90% finished. It's soon. But that's this work. So, just to start off, like a small introduction with Finn. So Finn.no has been doing personalization and recommender systems for a long time. And we use it in like a great variety of different products across the sites. We use it in personalized search. Of course, you have these recommender feeds on the front page, trying to find what you are mostly interested in. We use it for some sort of external ads. So if you have your house, you can get your house exposed in like VG or Facebook with using like for relevant people. And we do like a similar item recommendations on sort of the ad pages themselves. And so the way I want to talk about like a tiny bit of this, of course, and I want to frame this as a sort of a slate recommendation, is what we call it. So it's sort of this sequential interaction user and system platform. So you have a user, he enters the site, it's a very nice picture of a user there. We show him some recommendations. The user will then sort of look at the recommendations and will respond with a click, or not respond with a click. And this is sort of repeated. It will happen over and over again. And over time, you'll learn more about what the user is interested in. And sort of our task is to make these recommendations as relevant as possible for this user in as short amount of time as possible. Also, more introductions to the recommender systems, I'm sure all of you are aware of. But I mean, we usually, and certainly in this, we usually consider recommender systems in these high-dimensional spaces, right? So we sort of try to put all the users and all the items into some high-dimensional space. Here it's 2 dimensions. And sort of when you train our models, we get these kind of clusters. So we get like some areas are apartments in Oslo, other areas are maybe children clothing. And then we also try to put the users in there. And they can also, and the distance between like where we put the user and the item, sort of if the distance is short, the relevancy is higher and vice versa. And you can also have like, the user can sort of move around. You can have like a recurrent neural network where the users are moving around over time as he interacts with the platform. So that's a very high level overview. But sometimes, so after ChatGPT, there may be a different example here, but sometimes these sort of models go wrong. So this is in the case of the state-of-art image classifier. So here we have a state-of-art image classifier that correctly identifies that this image is of a pig. But we can only add like a super tiny amount of noise to this image, which is here, and we get this new image which looks exactly the same. And so like for our eyes, there is no difference there. But now, the model is even more certain that this is an airliner. So what happened? Well, it's clearly wrong. And I would say like in recommender systems, this is even a bigger problem. Because like a lot of people say we know everything about about our users, but in reality, we know very little. I think the median user we recommend to in Finn has like 5 clicks, which is more or less nothing. So it's like this. So here you have a user. So what should you recommend to this user? And you sort of glance over his previous clicks. You can sort of, he looked at cabins maybe in mountains. But then if you just look like 1 week later what this user looked at, then he looked at these things. which is completely different. I mean, there's like skis. Okay, he had cabins. Maybe that's the same thing. But I mean, he even looked at this dead otter. Would we be able to recommend this dead otter based on those 6 cabins? My argument is no. So this only says that there's a huge uncertainty in when we try to model our users, and we basically have no idea what they're interested in. We're sort of trying to do it anyways. But this means that we have a lot of uncertainty in our models, and that's why I'm going to pull up this very simple equation. And if that's sort of long, and this is sort of the uncertainty shows that there's 2 sort of sources of uncertainties in our models when we train them. And I would sort of say this is a Bayesian framework, but if you want to do it slightly simpler, you can do it in this way. So I mean, it's a probability whether it's a pig or a plane. Well, it sort of has two sources of uncertainty. It's sort of the data uncertainty and the model uncertainty. So I'll go through both of them quickly. So first, it's the data uncertainty. So that basically means that you haven't sort of collected enough, like your sensors of the world is not good enough. So if you imagine you would take a camera and point it at the sky, and you take a picture of something, and it's sort of blurred out what you took the picture of. So you can't really see what the picture is of. But I mean, if you have some super good statistical machine learning AI model, well, then you might be able to still classify this as a flying pig. So you might get a better camera to sort of reduce this data uncertainty. But of course, like we working in recommender systems, it's hard for us to just collect more user interactions with our users to train our recommender systems better. Because they will only interact with us like a certain amount of time. So there will be uncertainty here. And of course, we can collect better data. We can collect metadata on the users and on the items we have in our models. But you have this quote from saying that, like, in sort of in explicit recommender systems, but like, and it's really the collaborative filtering argument, right? Like even like a few more ratings on some kind of movie will sort of trump any metadata you can sort of use to sort of know more about this movie, which is sort of a surprising collaborative filtering fact. So it's hard. Very quickly, so what we have done in this case in Finn is that we realized that there's, like when you click and you do these interactions, it would be very useful to know what have the users considered whenever they were presented a recommendation or a list of recommendations. But when you looked in the literature, basically there's no open data sets that gives you this for free. There's like 3, I think, of them, but they are not really good for recommendations. So we open sourced, full anonymized, full disclaimer, but like 1 month of Finn data where you can show all the sort of the slates, so sort of the recommendation list people were presented and what they clicked on. So this is more information that you could use to sort of reduce this data uncertainty. The second source of uncertainty is sort of model uncertainty. And what is model uncertainty? Well, it's a highly Bayesian term. But basically it means that we have some uncertainty in what our parameters should be. So, and that sort of stems from limited user or item interactions. So here we're back in our high-dimensional recommender system space with some highly imaginary user names. None of them are present in the audience. But here we train the model, right? And we can see here, for instance, we have Olav, which is sort of placed in this area. And very close to Olav, there's an item from Finn of a bike. And there will be more bikes around here. And you see in the upper corner, you have Espen. And he's probably clicked on some sailboats because like he's close to the sailboats in our trained recommender system. So this is sort of our maximum likelihood estimate of where the users and items should be, and we can do recommendations from this. On the other hand, Olav hasn't interacted with like infinite number of bikes. So it might be actually, like if we sort of add the uncertainty of the parameter uncertainty, I mean, so the location of where Olav is in this space is a parameter, right, in the matrix factorization model. But if we don't have infinite number of interactions with him, we might actually be uncertain what like his true preference is. And the uncertainty might look something like this. So like still our maximum likelihood estimate, or sort of best guess of the preference of the user, thank you, Trattner, is still that he's interested in bikes. But there's some probability that he's also interested in sailboats. So our idea was to try to use this uncertainty. And now it's like, this is the explore, exploit uncertainty that James mentioned earlier, right? And that you should try to sort of use this uncertainty to know the true preferences. But our argument is that you can actually use this uncertainty to improve the recommendations. So, yeah, so we have fitted this with an approximate posterior groove for rec kind of model, is the details. But what we did was that, okay, we can sort of use this randomness. We don't only do 10 bikes for Olav, but we will do a bit of variety. And we will like not only sort of sometimes give him a full slate of bikes and sometimes give him a full slate of sailboats, but we'll do a little bit of both. So sort of within the same recommendation set, we will sample from this graph. So the first position might be a bike. The second position we recommend might be a sailboat. And the third position might be somewhere like whatever items are down here. And that gives a diversity in the list we will show him. And that's a technique we call in-slate Thompson sampling. And the result was that this works. So we gained like a 7% increase in the click rates when we used this in-slate Thompson sampling. And that's sort of good news, because now we're not only doing this exploration to sort of get better understand the preference of the user, but like we saw in James' talk, like this usually has a penalty in terms of relevancy on your recommendations. But since we can sort of do this in-slate thing where we sort of show in the same slate, we show a wide variety, like the chance that we will find something that's interesting to you in this recommendation is higher. And that's it. Thank you.
Waiting for the questions. There's one hand up here. Yeah, thanks.
Yes, I was wondering, how do you value a click? Because sometimes one click they can misclick and be 5 seconds, and other times there might be a cool thing from Facebook or something that people read, and how it messes your algorithm.
Yep. That's a much bigger question than I would have time for in 10 minutes. So, I mean, in this presentation, we do it simply and just call a click, and that's the value. In reality and Finn, and they're sitting there just next to you if you there's a like you value different conversion signals, clicks and everything into sort of something bigger, so you like have something to optimize. But yeah, it's a much bigger, like this is a very simplified version of it.
Okay, there's an idea.
So usually this run a transaction-based system where, let's say I'm trying to buy one cloth and I finished the cloth, like I bought the cloth, so transaction is finished. So the next recommendation item should not be the cloth. Or let's say I bought from Finn like table, and then once I transacted it will not be like table. How you handle that one?
We don't. So I guess the excuse for Finn is that we don't really know if the transaction happened or not. So instead, like Oda will present later, and they know, right? So they can do it, but it's harder for us.
Okay, one more question. I want to see arms. One more. Yes, please.
If you don't see the conversions, how you get this penalization? Like so basically you have like a user and bike and a boat, and then you show the boat, but you don't know what exactly happens after that, right?
Well, we know if they click, right? So that's sort of the main, I would say that's sort of the main feedback. And then also you have conversion signals on Finn, like you know that did they send a message to the seller, did they favorite it, and these kind of things. So even if you don't know the conversion or the transaction itself, you sort of know that the user showed more interest and click into this.
Okay, so basically what you have done is to have like history to know exactly like the correct clicks and the non-correct clicks to create a predictive model, different predictive model later.
To have tree?
Like you show the user the bike and the boat, okay, and the boat is a bit far and the bike is and then you saw, for instance, the user didn't click on the bike, clicked on the boat, for instance, okay.
Yeah.
So are
Yeah, I mean, yeah. Yeah, I mean, what happens if you click on a boat? I mean, then that goes back into your model. And in this case, it was a recurrent neural network that will sort of update with one more click. But I mean, you can also do this in matrix factorization setting, but I like retraining the model, but now you have one more piece of information on what the user prefers. Yeah. So then probably like Ola will move slightly up towards the boat. Yeah.
Okay, with that, I think we are done with the questions. Thank you so much.
Thank you.
All right. Okay, well, good morning still, everyone. My name is Alain Starke. I'm affiliated to both the University of Bergen, but also University of the Netherlands, Amsterdam in the Netherlands. Yeah, it's a session on fairness, right? And then it says psychology, so let's just get it out of the way. I'm a psychologist. And to wink a bit to the people who sometimes go to the Recommender System conference, here's a photo of me with a living donkey. I think only the people in the front row will get this joke. Anyway, I'm also a computer scientist, a bit of a communication scientist. And since I think there are a lot of computer scientists here, I want to bring the perspective a bit of the psychologist. And I want to advance psychologically informed recommender systems. Why? Because I'm writing a book chapter. I'll go back to that. But I think it's useful in domains where we're not necessarily only looking for taste, and we do care specifically about what people choose. So it's not just that we are looking for people click on anything, doesn't matter what, but we have some kind of idea about, yeah, what do we want them to click on as a system designer. On the other hand, the psychological perspective can help us to leverage or mitigate certain human biases that may help to, let's say, influence decisions, but also to steer them in a certain direction. The context of this talk is that we are preparing a book chapter, which has this very long title, together with Martijn Willemsen. And there we will show quite a few examples about how psychology can inform the design of recommender systems, both in terms of, let's say, algorithmic development and in terms of interface design. So here we have the two boxes. Or if you will, we have a couch and we have the image of this workshop. And I just want to show a few examples of how this can work. Because our goal is to make a case for when psychology can be relevant and how it can inform design of both your algorithms and your interfaces. And we think it's important to separate them from each other. Because on the one hand, you can change the content that is geared towards, let's say, what people click on, what they have interacted with. But on the other hand, how you present that content may already steer their preferences. As a psychologist, I need to sort of believe that preferences of humans are not fixed, that they are not stored in a database, but that they are very context dependent. You know, every decision, there is a lot of leeway, and we can, let's say, take them on the right or take them to the left. So, for example, what you could do is to take attitude and behavior models and take that as an input for how you would design a recommender system. But you can also just take, also a bit maybe the lazy way, what I did, take a psychological study that was fixed on one specific thing and then say, well, what would happen if we would apply it to multiple behaviors? So what would happen if it comes to a certain choice overload situation where a recommender system is actually useful? So this is an example of a psychologically informed algorithm design. This was a study on energy recommender systems. And on the one hand, we could determine people's energy-saving attitude, which was based on how many energy-saving measures you would take at home. On the other hand, we have a set of energy-saving measures, such as, well, maybe not so much in Norway, solar panels, but in the Netherlands or in Spain, it makes more sense from a, let's say, cost perspective to put solar panels on your rooftop. But you might also buy energy-efficient appliances. And psychology has then taught us that people might say that it's important to save energy, but they're not always motivated or able to actually do it. There are some behavioral costs involved. whether it's financially, whether it's motivationally, it doesn't really matter. And what we try to do in the study, including photos of myself, is to balance the recommendations in terms of, on the one hand, novelty, and on the other hand, feasibility. Because if you are saving energy and you're planning to do more, you're not in a standstill position. If you, let's say you have a very old home, it's not well insulated, then maybe after 1 year your home is better insulated, but you've taken a lot of measures. So according to our model, in the beginning you are, let's say, at the bottom of the scale, but you might progress at some point. And if you then just keep on recommending stuff from the bottom simply because a lot of people already do that, let's say the popular stuff, then it doesn't really help you to achieve behavioral change. And that's why, let's say, from an algorithmic point of view, this is very parametric, maybe even simplistic. But on the other hand, this perspective might actually help. Then on the, if we go to the interfaces, then we come at a different aspect. So with interfaces, I want to focus here a bit on nudges. So nudges would mean that you change the options, how they are presented in such a way that the choice becomes more predictable. So you could do that by highlighting something. You could do that by just re-ranking, you know, showing the thing at the top. So there was a very good paper from Jesse and Bjørnar that discusses digital nudging and recommender systems. And I want to highlight two different aspects. So that's to change the decision information and to change the decision structure. So changing decision information would, for example, be if you have a food recommender system that you really highlight the healthiness of the different recipes by showing maybe a label. You could also decide that if you are at a, I don't know, Starbucks is a thing, of course, or maybe if you're at Joe and the Juice, that you have 3 options of size for your coffee or for your juice, and that one, let's say the middle option is often a bit leaning towards either the large or the small option, just to make you push to buy the larger or the small option. You can also do that with the items that you're presenting. You can also make use of partitioning or defaults by, for example, it's a decision of the designer here, either based on the user model or not, whether you first show the healthier tab or whether you first show the unhealthy tab. And in this study, for example, we found that the labels didn't actually work so much in a personalized food recommender system, but whether we first showed the healthier tab or the unhealthier tab did increase healthiness of choices. So about these nudges, we also feel that they might lose their effectiveness if you are already doing this personalization. So we are in a room where we are quite good at that, and then we have all these psychological studies that tell us that, well, if you push here a little bit, then people's behavior might change. But what I've seen over the years is that if I apply, let's say, the same psychological studies to recommender systems, that it doesn't always work. It might lose their effectiveness. So I want to show an example from my Scandic hotel. Here it says, hang up your towel and make your mother smile. Mother Nature smile. Sorry, not your mother, Mother Nature. Maybe your mother would also be proud, right? Yeah. So this is, let's say, environmental nudge, right? Reuse your towel, etc. And I think each hotel has their own variety. But there was a psychological study in 2008 from Goldstein et al., and that investigated what if we don't say make Mother Nature smile, but what if we say a lot of other guests in this hotel were reusing their towel, or a lot of other guests in this exact hotel room with the same gender, whatnot, were reusing their towel. And they found that these social norms were more effective. So I thought, well, what if we do it for my energy recommender system? What if we show what other people are doing? I can predict that. I can use my user database. So changing the context from physical to digital, multiple behaviors, and also personalizing norms. So we consider the algorithm, and we consider the nudges. And then I built a recommender system, and I showed this percentage to customers of an energy supplier in the Netherlands called Eneco. And I showed for some energy saving measures like a majority of people was already doing this, and for others a smaller group. And then there were also conditions where I showed how much energy it would actually save. So we have a design with kilowatt hours, we have a design with social norms, and then the social norms differed in the list. So I thought, well, probably in the social norm condition, more energy would be saved in total. But this was not true. I did not find any link between that. But we did find that higher norms would get chosen more often. And there was no effect for showing, let's say, higher energy savings. So there was something to it, but the whole mechanism of the psychological study changed because, yeah, the energy-saving measures, they were no longer just towels, there were multiple things. And some things catered to the users and others didn't. So in this book chapter that we're going to write, we're going to try to look for explanations for that, and we're going to try to help people who work with recommender systems to do a better job in translating these psychological studies to the computer science domain. But I think an important perspective is that if something becomes personalized, these psychological things might no longer work, and we need to take that into account. So thank you, and I would love to have a chat.
Thank you very much, Alain, for a very nice talk. So where are the questions now to our psycholog? Yes.
Yes, Bjørnar from VG. There's state of mind has something to say on what you choose. So let's think about your healthy choices about food. And there will be a difference if a person is hungry or not.
Mm-hmm.
How does, as a psychologist, how do you do that kind of state of mind analysis when you test out your models?
Yeah, no, that's a very good question. So a psychologist would try to control as much as possible. So if, let's say, if hunger would play a role, then he would invite the participants around the same time of the day and, let's say, ask some control questions about that. But if you are running a recipe website, you don't want to do all of this stuff. I mean, let's say we want to cut out the questionnaires, right? We want to be able to predict that. I think as a psychologist, then, if you test multiple times of the day, then I would maybe also just use a data-driven prediction, like, okay, do people look at different things on different times of the day? And perhaps if they choose more, let's say if you are a designer that wants to promote healthiness, then maybe on some times of the day you want to push a bit more, show a few healthier options simply because you think that people are sort of at risk of choosing unhealthy content. But that's of course up to you, whether you think that matters for your specific application. But if you just control that and take that data as a factor, I think that's valid as a psychologist also to analyze.
All right. Are there more questions to Alain? Yes?
No.
Kim?
You said that it doesn't work when you do personalization. And so you think that it's a good idea to create a model based on psychology, but so the thing that confuses me a little bit, the way that I thought about using psychology in recommender systems were to say, as an input into the model. So I want to personalize this session, and this man is angry. And possibly I think about psychology like psychologists think about recommender system in very simple terms. But so in a sense that it's something you think about the state of a human, and you feed that into your algorithm, and then that's how you use the psychology more than the other way around.
Yeah, okay. I guess that, let's say, a lot of the applications that we had here are like social psychology, decision-making psychology. I guess if you're looking also at personality, I think then the recommender system community does quite something with also, with Big Five personality-driven. So let's say that's maybe where when I'm saying psychology-informed recommenders, that are maybe a bit overreaching, that maybe that's like a case where it does work. But I think mostly if you already filter the content and you try to then change how that content is presented, so those two categories that I had, I think there it's more limited what, let's say, the interface psychology can do. And I think there we should be, let's say, modest in our expectations. But when it comes to, let's say, if you really think about whether a user is angry, I think that's still a reasonable case, because that is very, it's like different. It's less related to, let's say, the structure of your information.
So I think you're underselling it, that's what I'm saying.
Sorry?
I think you're underselling it. I think psychology could
Yeah.
be a very important part in personalization.
That's okay.
Thank you very much
Thanks.
for the nice session.
Backside. I think it's fine. Maybe. Okay, so my name is Lemei, and I'm from NTNU Nordic Research Center. I'm a postdoc, and I'm working on recommender system and large-scale language model training. So today we're going to talk about how to adapt a language model paradigm for recommender systems. So from many examples today, such as ChatGPT and pre-trained BERT model and pre-trained transformer, and we can see maybe one fact that as the scale of the model increases, the performance improves, and meanwhile, many new capabilities are also unlocked. So one single model right now is more powerful than before and perform better than before. But how can we adapt such power to recommender systems? So to start with, we can learn from its training strategies. And language model training can be roughly divided into two different classes: the pre-trained fine-tuning classes and the prompt learning class. In pre-train and fine-tune paradigm, the pre-trained model can extract informative and transferable knowledge from abundant, unlabeled data. And benefits, this can be benefited to the downstream tasks, especially for the scenario that the labeled data for some domain is insufficient. So, and for some new domain that have overlap knowledge between the downstream tasks and the pre-trained model, can also avoid training a new model from scratch. And for prompt learning, it bridges the gap between the pre-trained and downstream objectives, and it allows to better utilize the rich knowledge from the pre-trained model, just similar as the previous one, but for prompt engineering, it only requires to adjust a small set of parameters. So it's more efficient. But both of these training types have the potential to solve the data sparsity and the resources scarcity problems that many recommender systems faces nowadays. However, when we try to do some work on that, we found that very few works are related to this topic, and they only covers a small number of BERT model and its variants and in recommendation usage, or it covers the self-supervised learning settings, also with some BERT model. They focus more on the model architecture, but none of them systematically analyze the relationship between different input data types and the training paradigms choices in the recommender systems. So recently, what we're doing is try to summarize the pre-trained language model-based recommender systems from the perspective of input data types, the training strategies, learning objectives, and we hope this can help for relevant practitioners and researchers to understand this nascent and rapidly developing field. So here we show a generic architecture of the pre-trained language model for recommendation. So specifically, it first collects a large amount of data from the data sources to pre-train the model. Then we can directly use this pre-trained model for inference, or we can fine-tune this pre-trained model with domain-specific data, or we can do prompt learning with expert knowledge for different downstream tasks, such as rating prediction, top key recommendation, conversational recommendation, as such that. And we find not only the textual data can be used for language model training paradigm in recommender systems. We can also train on the sequential data, such as user-item interaction and graph data, like user social graph, user-item interaction graph, and heterogeneous knowledge graph. And we can also train on multimodal data, such as image and textual data. So with this different data input, and our work is conducted mainly from the two perspectives. And figure B is the framework of our work, and we are not going to see that into detail. And we also did statistics on the numbers of publications recently on such topic in figure A. And we can see that as the language model become more popular, so as does the topic in recommender systems. So the traditional end-to-end training model can be classified into pre-training without fine-tune, but differently, it adapts the language model-based learning objectives into training phase, such as bird to rec. It takes user-item interactions as input and learns a bidirectional model via closed task, such as we also called like masked language modeling task which is quite different from traditional left-to-right learning ways. And some research works pre-train and fine-tune the model with different data sources. So, and in the fine-tuning process, the whole model parameter will be adjusted to achieve a better recommendation performance. Such as in this model, the API RecX, it pre-train and fine-tune the GPT model with different code libraries. And for the recommendation phase, and the GPT model will generate a list of APIs for recommendation. But considering the fine-tuning the whole model is usually very time-consuming and less flexible, so many researchers choose to fine-tune partial parameters of the pre-trained model to achieve a balance between the training overhead and the recommendation performance. So in this model, the UNIS rec, it fixes the parameters of the major architecture and only fine-tune a small proportion of parameters from the adapter when fusing embeddings from different scenarios for inductive or transductive recommendation. And some work also use a task-specific layer on top of the pre-trained model, and only fine-tune this task-specific layer for recommendation purpose, which is more efficient. So for instance, for this GBERT model, it includes 3 parts: the graph neural network, and to learn the ontology embeddings from the ontology tree. And then this embedding will be used as input to pre-train a BERT model to get the embeddings of the medical code from user house record. And then the fine-tuning process only goes through adjusting the parameters of the classifier. But for supervised learning in recommendation tasks, one problem is that the lack of large labeled data for some domains. So prompt learning can help to solve this problem by transferring the domain knowledge introduced through prompts. So, however, when we consider to leverage this technique to recommendation scenarios, we meet several challenges. The first is in natural language processing, the inputs are textual data. So they usually have the semantic meanings. But for a sequence of items, they may not have concrete explainable semantics. And the second challenge is how to personalize the output in the prompt learning phase. So the prompts, there are 2 different types of prompts. The first we can see here, this example is the discrete, or we call it hard prompts. So barely it's used a sequence of the readable words, such as like GDK is developed by, and the model will generate Oracle. And this is a super long text, and the model will generate the summary. So BERT can, these are discrete prompts, but we also have soft continuous prompts represented as continuous vectors, but we are not sure what the meaning of that. And for prompt tuning, we can fix the pre-trained model, but only tune the prompt generator to perform the personalized, to generate the personalized prompts for personalization in recommendation purpose. And for several special designed prompts, especially when we use the human expert, and some work choose to tune the pre-trained model to steer the recommendation tasks. And for instances, this Unimind model. But another example for prompting paradigm is zero-shot recommendation. And it directly generates the results of recommendation and related subtasks without changing the parameters of the pre-trained model or prompt. And the output is barely based on the input of the prompt. So the P5 model is falling in this category. But of course, you can tune both the pre-trained model and the prompts to perform to achieve a better recommendation performance. But you need to consider the balance between the overhead and the performance. Okay. And we know there are many language modeling objectives, language learning objectives, such as if we train GPT model, they use autoregressive modeling from left to right side, just we read the as we read the paper or we read the book. And we also can use the mask language modeling, such as clause task, and for BERT, next sentence prediction for BERT, and replace the token detection, just for the recommendation tasks. But we also can adapt such different learning objectives into different recommendation purpose, such as for graph-based recommendation, we can adapt mask language modeling for mask node or edge prediction. And of course, this is a very new domain, so we have a lot of open issues and future research direction. First of all is language bias and fact inconsistency in the language generation tasks, especially in conversational recommender systems and explainable recommender systems. So how to enhance the diversity and pertinence of generated explanation, and replies the influent responses rather than just we call it Tai Chi responses because it's all repetitive and barely have nothing informative in the responses. So how can we deal with that? And also we are not sure the knowledge transfer mechanism right now. How we can inject different knowledge into pre-training phase and to help to improve the performance in the downstream tasks is also a problem. And for, because we know that the pre-trained language model are very large, and so it's kind of very hard to tune when the new data comes in. So how to maintain and update such complex and large-scale models without affecting the efficiency and accuracy of the recommendations is also a problem. And last is the privacy issue, because some researchers already reveal that some pre-trained model can generate the user gender and age, so predict the user gender and age. So this raises the privacy issues of this domain. So if you want more detail of this domain, and you can just refer to our paper. So thank you.
One rapid question. Yes, please.
Hi, my name is Kim. I was the one down front that asked all the questions before. So right now, the ChatGPT, you talk about evaluation, and it has been awesome marketing, but it's full of mistakes. Do you think that we should take that and use it as recommender systems also? Because I understand that they have trained it and made it great, but the prompting, how would you actually implement that in a recommender system, and how would we evaluate whether it's good? Because right now, everybody is jumping on the vacuum to use it, but nobody knows how it will actually work because there is no good way of
if you talk about the ChatGPT, the natural language processing phase, the text generation problem, and I think I haven't done the deep investigation on that, but I know that the evaluation part is quite hard because it should include a lot of stuff like fluency, like accuracy of that. It's really hard accuracy, and very few works related to this. And they have some works done, but only a few works related to this. And they only consider from different perspectives, and some of them have a large implementation overhead. So this is an open issue, I should say. Hasn't been solved. But for if you ask how to use the prompt learning method into the recommender systems, and the most likely one with ChatGPT is this P5 model, I think, because it's learned from different prompts input, and the output is also different tasks according to the input prompts. So you don't need to fine-tune it. You just trained with prompt and with unlabeled data, or maybe labeled data in recommender systems. And then it will generate automatically after you trained. Yeah, so you can refer to, yeah.
Thank you very much again. Very good. As Arnoldo said, well, different world, I don't know, but I hope you're ready to hear a little bit about medicine and personalized treatment. So my name is Moa Myklebust. I'm a PhD candidate at Oslo Center for Biostatistics and Epidemiology. And my talk is titled Personalized Treatment Recommendation for Multiple Myeloma Patient. Then first of all, what is multiple myeloma? It is a type of cancer that originates in the bone marrow that you can see a picture of here. And it starts in a type of white blood cells called plasma cells that usually produce antibodies that help the body. But when these have mutated and become multiple myeloma cells, they produce useless antibodies that are, in fact, they produce so many of them that they are harmful for the body. But this also means that you can take a blood sample and measure the amount of these useless antibodies in the blood. And in this way, you can monitor the disease course of a patient over time. So I will show you now the history of one patient, and I will walk you through this plot because I don't think you've seen it before. So the x-axis is years since diagnosis for this one patient. And then these black crosses are these useless antibodies or M protein over time. And on the other y-axis, you have the drugs. So colored bar means that this drug is active in this period of time. So for this patient, you can see that first, it is given a combination of 4 drugs. One of them is stopped early, and then the 3 are continued for a while, with the effect that the cancer reduces in size for a while. Then the treatment is stopped and it comes back up again. And at that point, 3 new drugs are given for a longer time. The cancer reacts to this, reduces in size, and then comes back up again. And it comes back up again while the patient is still on treatment. And the reason for this is that the cancer has become resistant to these drugs in this time. Now, if we could, at the time before we gave this new treatment combination, predict this response, this could be very useful in decision making. Because you see, like, I have included 18 drugs on the side. So these 3 drugs is not the only possible combination, but you could imagine other combinations. And this is not a trivial setting, like we cannot do just exploration and explore what we want, but we must always, at every time point, give the patient the best thing for them. So if we could predict this response in advance, it would be nice. So it's going to be a little bit of a way how we get there, so bear with me. First, I will say that now we can model this shape of the response. Okay, sorry, different order. Yeah, the general idea then first. If you have multiple of these patients, then, and you also know something more about them, like their ages and their preconditions and things, can we then make a machine learning model where for a new patient, you make a treatment prediction of this response? So now we are here. This is the one I was going to show you. Here we have modeled this total amount of protein as a sum of two populations. One is this red line, which is a resistant population that is growing all the time from a small initial percentage. And then on top you have some sensitive cells that are dying under treatment. So this gives you three parameters. Pi is the fraction of resistant cells in the beginning. Rho is the growth rate of the resistant cells. And alpha is the decay rate of the sensitive cells. And this very simple model gives you the flexibility you need to capture all sorts of different responses that these patients can have. So all these patients can fit within like this model. And the idea is, if you have these different patients, and we focus first on this green period. Here the green is like one combination of drugs. Then for each interval that each patient received this combination, you can estimate the parameters within that region. And then you look at whatever happened before this interval. And you take the patient's age before that and their things you measure in their blood and also the previous treatments that they received. And you generate a set of covariates that represents this past history. Now, if you can do this, then the question is how can you make a model that takes these covariates and predicts these three parameters for each patient? This is sort of the way we formulate it. Now, this is only for the green treatment combination. But if you have a new patient now that you want to make a prediction for, first you generate their covariates, and then you pass them through this prediction model, which can then give you a mechanistic prediction of how the patient will respond to this treatment. And in order to make a choice between treatments, you also need a model for another type of treatment combination. And then in this case, you see that the yellow treatment is better, so we suggest that. So I don't have time for the details on how we do this, but I will just say for the statisticians in the room that it's a hierarchical Bayesian model, and we do some Bayesian inference on this so that you get nice uncertainties on their estimates. These are some results from a simulation study that we did, where we simulate like 100 patients and see if we can make this work, which we can. In this case, you see, so the red line is the true resistant part of the protein, and the light blue line is the true total protein. And these colored bars are the confidence intervals, or credible intervals. So this is a patient in the training data, and you can see that we match the observation quite well. But more importantly, we also make this work for prediction in simulated cases. So that's the simulated data that we have to show you today. This is a work in progress, and in order to be relevant for clinical decision making, we need to have the most updated data sets. And I thought I would just mention that thanks to policies of sharing data after clinical trials, even from pharmaceutical companies, we have been able to start a process of getting access to data sets that compare very new and interesting combinations of treatments. And I would just ask you to stay tuned, because we will dig into this data and come back with the results when we have them. Thank you very much. And these are our collaborators. Yeah.
Thank you, Even. Question or comment? Yes, please.
So in recommender systems, there's a lot of talk about explainability and that you sometimes need to be able to explain why you made a certain recommendation. I assume that's important for you guys as well.
Very much.
You want to be able to explain why you went with a treatment. How do you think about that?
That's very true. So you can make different models for how you predict this response. And the simplest is like a linear model, where you can very easily see sort of which covariates made this happen. But then I think the most natural would be to use Shapley values or something when you have more complex models. So this is, yeah, sort of the best thing.
Do you have hard requirements on it?
If we have
hard requirements on explainability from like the hospital or something?
I don't know. Do you know? Not hard requirement. No. I think it's
from the EU, you're going to get some requirements.
Yeah. Well, definitely. But like, how hard are they? I don't know.
You have a question?
Yes, but now I forgot it.
Okay.
What are your thoughts on the possibility of overfitting a model like this, since you have so much data and the confidence it won't look so nice and tidy?
Yeah. So you have maybe few patients, like you always have 2 or 3 patients. And so you need to ask the model to have sparse and like very like not over-eager solution. We cannot have this optimism thing maybe. So it's always a problem, but you must handle it using cross-validation and all these things to combat it, of course. Yeah.
One more question there.
Yeah, I see in your graph that 400 days in order to start to get like good prediction accuracy. Are you trying to at least, because 1 year is not small when it comes to cancer efficiency?
Yeah, so this is we would like to have more often like this sampling of these measurements, but we don't have that. They usually wait like several months in between the samples. But since we have patients that have histories that are last several years, we can use that data in this way.
So you are trying to decrease this duration, because as I said, like it's taking 400 days in order to start to have like a good prediction when it's.
I'm not sure which plot is this.
Or maybe I misinterpreted. Yeah, this one, 600 days.
This one. Oh, so okay. So this blue part is the sum of this red part and something else that adds to the blue part. So if you compare the light blue line to the darker blue bands, that's sort of the comparison you have to be making.
I'm comparing the red line with the blue line. Oh, that's wrong.
Yeah, that's not how it's supposed to be. You compare the red line to these orange ones, and then you compare the blue line to the blue ones. I can show you, yeah.
By magic, we have an updated program now.
All right, I'll start. Hello, my name is Lars. I'm a data scientist at ODA. And together with Johannes, which is here, and Fredrik, we make the recommendation models at ODA. So today I'll kind of walk through and see the different models that we have, and more specifically how kind of we can use representation learning in our kind of product development of making good recommendations for our users. So I kind of assume some of you know ODA, but if not, this is kind of our short value proposition. We build the world's most effective retail system to give people more space for life. That involves kind of personalizing and giving good recommendations to your online grocery shopping. So when you enter our store in the app or web, you have a lot of questions or problems that you want to solve. It's a quite of daunting task to do your groceries. But you have a lot of problems. You want to find all your staples, the thing you buy every week, your milk and bread. You want to find what's for dinner. You want to plan your week, what's all the meals. Sometimes you want to find a new item, some inspiration, some recipes, or you just want to browse the assortment. So it's kind of a lot of problems you have when you enter a store. It's a very multimodal, so we kind of have to address all of this. Then we want to personalize that experience as a whole. So our job as data scientists is kind of identifying these problems and kind of help them plan their week, do the thinking for them in order to kind of solve the planning problem of grocery shopping. And to do that, we have to kind of take the problems, predict the problems the user have, and translate them into predictions problems where we can kind of effectively give recommendations. And ultimately, we want to do this to give people more space for life, don't think about groceries. So how can we approach this? What do we need to model? What do we need to have in order to do some inference? So it's kind of three things we need to know, three entities that we can reason about. First thing, it's the product themselves. Secondly, we have lists. Lists can be like your current cart. It can be some recipe, your order history, or your shopping list. And we have the user. And if we can model this, we can build applications. And kind of our hypothesis is that if we can kind of learn meaningful representations for all these entities, we can build a wide range of different recommender systems downstream. So in the rest of the talk, I'll kind of go through each of these entities and give examples of how we approach this problem. So first off, we start with the product part of it, where we want to learn product embeddings. And we kind of have luxury now that we have a lot of data, and we want to put the model where the data really scales. So we have, of course, like a lot of meta information on the product, but that is static. Like every week, every day, we get thousands of new orders. That's more and more data where the user kind of neatly organizes the product relationships into clear, collectible data items. So we kind of want to use the orders to learn embeddings. And how we do that, we can take a lot of inspiration from language models. So in language models, you typically have a corpus of sentences, and then you can use a model like this, Word2Vec. It's a model that have existed for 10 years now, kind of that embeds the sentences or the words into this vector space where you can do inference, make similarity comparisons. So when we do this, we just speak the language of products. So if each sentence is an order and each word is a product ID, we can just do this out of the box and model this. This works really well. We get this product embeddings, and then we can do a lot of comparisons with us. So all the kind of ice creams would be in one place in that space, and you can do a lot of inference. So the most straightforward application you can do this is kind of do similar items recommendations. So at the product, you want to explore what similar items. You want to explore the assortment. So in this case, you're at tofu. You can browse. You see there's other tofus. Further down the list, you see like soy sauce. You see coconut milk. You go in there, and then you can further on browse, explore the assortment, and kind of have like a Pinterest browsing experience. Second kind of application for this is what do we do with new products? I mean, new products don't have transactional data, so we can't do the same approach. But we have some stuff. We have the text of the product. We have the category information. We have price. We have a lot of meta information. So Sylvia, my colleague here, built a model that kind of takes this information and then predicts the product embeddings. And then you're in the same space. You can do this operations and personalize new products by not having any transactional data. A third application of this is, okay, you want to find some new special product. You want to have a bit of serendipity. You want to discover the assortment. How can you use product embeddings to build an application like that? So you can do that basically in 3 steps. First, you kind of look through your order history, kind of find those identifying products. Then you can use the product embeddings to kind of branch out, find candidates that are similar, and then rank them in a new sense, and then kind of give a feed that is inspiring but still personalized. Okay, what do we do for lists? This is a different entity to model. So one example is a recipe, that is a list of products. And there we have a lot of questions like, okay, I want to find a recipe that's similar to what's in the cart, or a recipe based on my order history, or a recipe that is similar to this recipe. So then we need to compare lists of products. A very straightforward solution to do this, which works surprisingly well, is just to aggregate the product embeddings. Aggregate across the dimension and then do the same operations. You can even do the mean aggregation. You can do a bit more fancy. You can take a weighted mean based on some TF-IDF score, and then it works pretty well out of the box. But this also have a downside, like it doesn't model the cross-product relationships. So in this case, we want to do a bit more sophisticated solution. You want to kind of use the sequential information in a sequence to predict what's next. So we have a model for this, a next item prediction. And then we can kind of train a model that takes the current cart or a masked out part of the cart and then predicts left to right what's the next product. We use a transformer model for this. And the good thing about this as well, when we build a product around it, it can update every time you add something to the cart. So then we can build a product that revolves around the action the user takes and the response the recommendation model gives. Then it can kind of be on help you along the entire trajectory of your building the cart and then checking out at the end. And then serve it live and update as it goes. Lastly, we have our kind of biggest model for what do we do when we have considered the user. And the user means a lot of stuff. You have the metadata on the user. But more importantly, you have kind of the order history. So the order history is kind of a list of previous orders. And you want to kind of predict what the user is going to buy at their next order. So when they enter the shop, they can find all their products that are relevant and they can just click through it. So you also use a transformer-like model for this, where we have the order history at the bottom here. And then you have some user representation based on the meta or the contextual information about the user. And we model this as a kind of a classification task where we sample a product, a target product, and then the task to be solved is kind of, is the user buying this at the next order? And then we can sample both positive and negative products and then learn what kind of products the user likes and prefers. This also have the benefit that it's kind of takes in the shopping carts, the contextual information about the user. It first then transform the sequence, get a kind of user embedding, and then it downstream has a classification model if this is the product that the user wants or not. Right. That was some insights on the models that we have. I'm going to kind of sum up a bit. So the kind of benefit of doing this representation learning is that we can kind of focus our effort into making good representation of these entities, and kind of focus on these entities, and then we can build more recommendation models on top downstream. And then it's also easier to iterate and kind of integrate into the product development of our product as a whole. Added bonus of this is that these representations can be shared to others across the company, and it can and have been used in like other data science application, whether it's pricing or behavioral segmentation or whatnot, and then it can help to improve other models as well. Yes, this was it. Thanks.
Thank you for the interesting talk. So I want just to ask you, how do you handle the cold start problem? When there is new items, new users, how you personalize for
right.
For that case?
Yeah. So, I mean, there's several different kinds of cold start, right? I addressed what you do when a new product enters the store. Yeah. Then we can already do some things because we have the text of the product that we can use. We just use a pre-trained BERT to embed the text. We also have like meta information on the product. And then we also can predict the embedding feature, as I showed. But then cold start for users is difficult as well. We don't have the order history. What we can do is a model like this that kind of reacts on the cart. So if you're a new user, you can add stuff to your cart, and then we use what's in the cart to give recommendations live. Yeah.
Hi, Linn is also from Starke. Do you see any difference in how these algorithms perform across different user segments or geographies? I mean, are people in Berlin responding as well as the ones in Oslo?
So, I mean, in Norway, we have a lot more data. So they perform better. And then, as we've seen, like we launched in Finland as well, they improve over time. So we launch them, and then we see that the model is getting better and better with more data. In Berlin, we don't really have a lot of recommendations yet because there's not a lot of data. Yeah.
Good, thank you very much.
Okay, my name is Øystein. I'm a data science, data engineer consultant at Supersteria. However, I will be presenting my master's thesis that I completed for University of Oslo, along with my supervisors Ida Scheel, Stefan Wender, and Simen Eide. As you can see, this was written in August of 2021, and I have not been working with recommender systems since, so I leave that as a warning if I make any claims in general about recommendation systems, as it's a quickly moving field, and I have not really read up on it since. But hopefully, this model will give some insights that can be useful to you. Okay, so firstly, we'll go over some motivation for our model, our data, the model that we introduce, and some of the results. So firstly, recommendation, we see it as a time process. So users make some actions over time. In our case, we look at clicks on ads. So here we have the event of a user clicking on an ad through time. This is a discrete process and discrete selections. And we want to predict the interest of the user at that time, which is in general the recommendation problem, but we want to give more sort of explainable interest predictions. So what we do is we say that our observed clicks is the result of a hidden variable that we do not observe that are the interests. So instead of saying that a previous click depends on, or the next click depends on the previous click, a click event is just a result of a user interest. And that interest can evolve over time, and it will result in different clicks. That results in, hopefully, an interpretable model, so that we can look at the interest instead of looking at a sort of random
sample from that interest in the click. But to sort of achieve this in a reasonable amount of time, we do ignore some recommendation complexities. So we do not look at recommending an optimal set or anything. We just want to know what is the probability of a user clicking on an item. So our data set is collected from FIM. We limit it to car ads and include 2 months of clicks. We also exclude some rare items and users to create a more dense data set. Now this is not extremely dense, I think, but it's less sort of sparse than Torget and other areas of Finn. So what do? We use a hidden Markov model to model user behavior. So hidden Markov model describes a sequential process of a set amount of interest and a set amount of items for observed and hidden data. And what this model does is it assumes a Markov property on the hidden interests. So when the interests evolve over time, the next interests is only dependent on the previous interest. So if you're in interest K or interest L at time t, then there's just a set vector of probabilities that define what is the interest that you're likely in the next time step. You also have to define the probability of which interest you're in at time 1, but we will not look too much into this. It's just a sort of a nuisance parameter. And then we need an emission distribution. This defines how our observations depend on this hidden sort of evolution of interest. So in our case, we just use a multinomial distribution. Given a interest, there's a set probability of user clicking on an item. Now, all of these transition probabilities, selection probabilities, and initial state probabilities are parameters that need to be defined. In addition, we don't know the user interest at any time interval. So this is quite a complex optimization process to try to find the maximum likelihood estimators of both a reasonable interest when we have no information of what interest might exist. We don't know how interests evolve, and we don't know what interests users belong to. However, there are optimization equations for Markov models. However, with recommendation datasets, they're usually difficult to use because there's an incredible amount of parameters in the selection matrix. So here we have interests, k interests on the rows, and along the columns you have all items of the dataset. And you can imagine if you don't simplify this matrix, every time we add an interest, we add n parameters, or equal to the number of items in the dataset. So in our case, that's over 100,000 items. So every time we want to add an interest, we add 100,000 parameters to our dataset. However, we do expect both similar interests and similar items. So some of you might recognize this matrix. It's very similar to matrix factorization, where you have users and items. Instead, we have interests and items. So we can use matrix factorization to simplify this matrix. And we circumvent the issue that usually applies to matrix factorization, where you have sort of a static prediction, where a lot of papers are written on sort of applying heuristics to matrix factorization to allow the evolution of an interest. Instead, we say, no, the interests are static, but we allow users to move between these interests to sort of fit evolving interests of users. Now, we also did vectorization and batching and moved the fit over to the GPU to sort of circumvent the linear nature of optimizing a hidden Markov model. We simplified online predictions, however, it's still comparatively slow. It's not really a useful recommendation model, at least not yet. So we did not focus on making the predictions good. So it does recognize interest to some extent, however, the prediction or the recommendation performance and online testing is not great. However, we do get automatic sort of group clustering of interests along with predictions of what interests users are in at different times. How much time is left? Plenty? Yes, okay. So what is great here is that we both have the performance of the model when it performs as a predictor. So the top plot is only given past data. But if you want to perform some sort of analysis on a data set, you don't just have past data, you have future data as well. So you can use the future data to inform the model of where interests might actually have changed. So we can go over some more examples, some more interesting ones. As here is just, it clicks on some BMWs and then a different model of BMW, and some interest state has a higher sort of probability of clicking that second BMW. So there's a switch there, but it's not very interesting. Here it's a bit more interesting, as it's very clear at the beginning that a user has a specific interest. It's a Hyundai Kona off-road car. I don't know. But when it performs as a predictor, when the user starts exploring a bit more, the predictor is a bit unsure in the beginning, which is reasonable. If you look at these initial cars, you don't really know what the user is looking for. However, we see that this type of car that is throughout this session is quite consistent. So when we include future data as well, we can get a user session that has very clean transition between two probabilities, or two states, two interests. So this is more exploratory behavior. Here, the model never really lands on a specific interest. And this sort of underlines the complexity in defining what an interest is. So should the model actually have a specific interest for this exploratory behavior at the beginning? Or should it say that, no, we have a bunch of different interests and users can be in a state where they're sort of just clicking around and don't really belong to an interest? And that is more of a definition problem. It's difficult to say what is correct. But that also underlines sort of why it's useful to have a model do this work for you. Because then you don't have to sort of have people define what are groups that exist in your data set, what are interest changes. The sort of model just optimizes to what is most likely given your data set and given your limitations on number of states and number of, or the embedding dimension in the matrix vectorization. So here is another sort of session where the prediction model does predict the change in interest. However, given future data, it sort of flattens out, and we said that the user didn't really change their interests at all throughout the session, which does sort of make sense. It's sort of sedans and station wagons throughout. Now this one is a bit more interesting. Here you see some sort of back and forth between interests. That is also questionable whether that is reasonable. You could say that all of this should be one interest of exploratory behavior, but that is something that occurs as well. It should also be noted that these sessions are selected from the top 50 sessions in our test set, so they're not cherry-picked. They're just excluding sessions that sort of show the same as previous sessions. But one really interesting factor or thing is that when we compare models with a lot of interest states and a few interest states, the changes in interest or position of changing interests are the same or very similar. And when we go further down into more complex sessions, this is the same case as well. And what we in fact do see, and we'll go into this a bit later, I'll just go over the model predictions today. Go over the prediction first, and then we'll go over the conclusion to why these different session numbers are similar and why that's interesting. So we see these interests plots throughout user sessions, and we automatically get interest groups, user classification through these interest groups, which enables easy correlation between other factors you can observe, or other factors you observe. So if you want to say, what are interests that make it more likely for users to leave my site? Just take the observation of users leaving the site, correlate that to the predicted user interests, and then you'll get what interests you sort of are least optimal in. So you can find interests where you should be improving in your site. If you have a static catalog, you can also do long-term interest trends automatically on these automatically recognized interest groups. However, obviously the predictions themselves as a recommender are popularity dependent, have low variation, and sensitive to outliers. So as a prediction model or recommendation model, it's not very good. However, here we look at the transition matrix. This is the probability of the transitioning between different states.
Now we see that this plot is split into two. That is the diagonal element, which are the probability of transitioning to the same state, so staying in your same interests. And we see that this probability is around 0.8 to 0.95, and that is consistent for different number of states. So that means that even if you have a more complex model, the positions of the interest changes stay the same, which sort of indicates that interest changes are something that exists, are some real events that exist in just click data, and it's not some sort of event that is just dependent on how complex your model is. Because that's what I expected when I started working on this, is you choose how many interest changes you predict by just having a more complex model. But actually it seems like interest changes are real events that exist in data and that you can sort of extract and analyze. And one other interesting correlation is that the sort of short memoriness of a lot of recommenders seem to correlate to this, the time users spend in single interests. So we see that the amount of the user history length that is useful for prediction is around 10 or a little over. And that relates quite well to the transition matrix, which means that recommenders really only use, or at least in this case, really only use the data for the current interests. And it's very difficult to sort of generalize previous interests into a new interest and predictions for that new interest. So in conclusion, we have combined a hidden marker model and matrix factorization to give insightful sort of evolution of interests through time for users by automatically recognizing what interest groups exists with your set number of interest groups that you want to fit, and also then giving a evolution between these interest states. It gives acceptable recommendation performance, however, it's not the main focus. The most interesting part is that it gives sensible interest modeling, and it makes it easy to explore how user interest evolves and being able to correlate user interest with other factors that you observe in your site, like setting a sort of monitoring solution on are we suddenly doing worse for certain interest groups, where that sort of work can be enabled by this recommendation model. Thank you.
Again, one question, please.
When you were doing this work or when you found out that these interests are actually like a real change, did you get any feeling for whether there's something happening to the user, like they go to sleep and then they wake up and then they do something new, or is it that they're actually learning from their browsing experience, that they're like looking for this one car, finding out that no, I actually need this other kind of car, and then they sort of swap interests?
I think that's a really interesting.
Changing them, or is it like them changing and coming back as a new person?
I think that's a really interesting question. I don't know, but it can be solved by making the transition function more complex. So you can sort of introduce a time factor through that transition matrix so that the probabilities of transitioning between states can depend on the time between clicks. And then you can use that to analyze whether what you say is that some transitions happen maybe throughout a long time interval. So maybe sleeping introduce some transitions, and maybe other transitions are something you learn quickly. So that is something you can find out using this model, but I have not done sort of that analysis.
Good, thank you very much.
Yes, hello, my name is Thomas Oldervoll. I'm a consultant for Senior, but the last few years I've worked at the recommendations team at NRK with Linn, Cecilie Solbergersen, who's a data scientist at the same team. And we're actually not going to talk about news personalization as such, because we're mostly going to focus on podcasts, radio, and TV content. But I hope you remember the keynote this morning from James Grant, because in practice we're going to talk about how we do the stuff that he talked about in practice.
Yeah. Yes.
So all of you Norwegians in the audience, I guess, know NRK very well. But for those of you who don't, we are the Norwegian public broadcaster. And in addition to traditional TV channels and radio channels, we have these services. So our streaming services, NRK TV and NRK Radio, our news website, nrk.no, and our kids streaming service, NRK Super. As Thomas mentioned, we are going to focus today on NRK TV and NRK Radio and what we have done on Bandits and personalization there. As a public broadcaster, it is important to mention that we have a mission, an objective, or a mandate, if you will, to not only entertain, but also to strengthen the democracy, to highlight culture, and also to bring everyone in Norway together. And this, especially this last one here, is a bit contradictory, right, to personalization, because it's all about bringing people together and be unifying. So we have to find a way to provide relevance to the individual, while at the same time being important for everyone in Norway as a whole. And to do this, we think of publishing on 3 levels. So we have this first one, which is for everyone. This one is editorially managed. Here we have breaking news and all of the content that is relevant and important for everyone to know. Then we have the second level, where we place users into segments and recommend content for that segment. And then the third one is the personalized level, where content is recommended especially to you as a user. And I will say a little bit about this segmented level and what we have done with segmented sections in NRK TV. So for certain sections that already exist in NRK TV on the front page in NRK TV, we want to sort the sections such that the content that is most relevant for the segment appears in the front of the list. And to do this, we want to use Bandit, and more specifically Thomson sampling, to get this nice balance of exploration and exploitation, as we have heard about earlier. What we basically do is that we count the number of successes and failures for each title in the list. So if a user clicks and consumes Eagles will get a success, and all of the other titles that were shown at the same time will get a failure. Having gathered these data, we can then assume that the probability of reward can be modeled through a beta distribution. So it might look something like this, where we get one distribution for each item, and then sampling from these distributions determine the sorting of the list. And for these segmented sections, as we call them, we have a quite simple approach where we have one bandit for each segment, such that section and segment combined is considered as the context. And for this, we do not even learn across context, so only the data gathered from the section and given segment is used to sort the list. And we have experimented a lot with this and running a lot of A/B tests as well. And here are some results where we compare the original sorting with the bandit sorting. And what we observe is basically that users both click and consume much significantly more from this section when bandit is turned on. And of course, we achieve a lot more dynamic and variation in what is exposed to the user, which is also something that we want. And from just looking at the sections for the different segments, we also see that they give a quite different impression depending on what segment you are in. So that is, of course, also something that we want when we are doing this segmentation. And finally, we have also observed some other cool properties of using bandits in general, like this example with Atlantic Crossing. At the time we observed this, Atlantic Crossing was a quite old TV series. It was published 1 year before, so it was not exposed a lot on the NRK TV front page at all, but was placed far, far back in one of the sections where we had a bandit turned on. And then suddenly one day, it was made a huge jump to the front of the list, and none of us knew what was happening before we read the news and saw that Atlantic Crossing got an International Emmy Award the day before. So Bandit kind of discovered this all by itself, and before the editorial desk even started to promote it as well. So this with the segmentation is we have taken a very easy approach that has been good for us because it has been easy to communicate within the organization, which has been very important, and also been a very nice place for us to start playing around with bandits.
Yes. Then the next step for us is to look at the innermost level here, the third level, the fully personalized level. And then there we have started in the radio service. It was the first spot in the service where we started doing this. And these are the, so there we have one section that is the fully personalized section. And so there every individual user will get their own list, and this is my list at the top and then Cecilia's list at the bottom for the very first version of this. Then there's some issues because we can't just use the same approach that we did for the segmented sections that Cecilia talked about, because she mentioned that the context in those sections were the combination of segment and section ID. So in here we only have one section, but for context we actually use every single individual user. So instead of having like in practice 50 contexts, we now have millions of contexts because we have more than 1 million users. And for the Bandit, the Bandit's task is to choose the right action given a context. And when we only learn to collect the data per context, that's we get way too sparse data. So we don't learn enough about each context. So we have to start sharing data across contexts so that we exploit the knowledge we have gained from exploring in other contexts. So that's therefore we need to go from the Bandit per context approach to a full contextual Bandit. And for the Bandit per context, we developed the whole thing ourselves from scratch pretty much. But when we consider doing that for the contextual Bandit too, but there's lots of nice features we would want. So then we started looking at what kind of libraries exist out there. And then we found this one, Wabbit. That, despite the funny name, is actually a pretty serious library. So it is maintained and used by Microsoft. It's part of their Azure Personalizer service, and they also use it for things like the Xbox front page, I think. And the team behind it, John Langford is the main guy. They publish papers about like new exploration strategies and so on. So we can get lots of good stuff, we think, from Wabbit. Different exploration strategies, different model types like linear regression. We can add feature crosses, or we can go to a full neural network. It has support for offline evaluation with these fancy adjustments like IPS and doubly robust that people keep talking about at Rexis all the time. It can do online learning, not just batch, and And an important part for us is that it also supports both Python and Scala, because our serving system is in Scala, but we would like to use Python for the modeling and training. The particular type of Bandit we're using for in WAPL is what they call conditional contextual Bandit, where you normally a Bandit you choose a single action, but we want to. In our case, an action is a podcast, for instance. It's one. We call it plugs in a section. One content item. But we want to show a list of content. So then what this does, this is similar to the slates that Simen talked about, where but first you pick an item for the first slot, and then for the second slot you can choose among any candidate except the one that you already used for the first slot, and then for the third slot you exclude the two first, etc. So this is all built into WAPL Rabbit, which was handy for us. So how we use this is that we start out with a pool of potential recommendations, everything that can be recommended in this section. And that's, in practice, we have 300 titles, 300 podcasts and radio series that can be recommended. But most of those are probably irrelevant for this particular user. So then we use a collaborative filtering model that we already had. We use ALS in practice, alternating least squares for the collaborative filtering model. So then we take the 30 most relevant titles for this user. And that's what we feed into WAPL Rabbit as the candidate actions. And then WAPL Rabbit will then choose, it will sort the list and choose the top 20 top actions. And that's what we return out to the client. And in practice, and it's an ordered list. So in practice, the client will show maybe typically only 3 of them to the user unless they scroll, which in practice most users don't. So it's important to find the very, very best actions among that list. Yeah. So that's basically that's what we have out in production right now, but we have lots of stuff in the pipeline. Very soon we will launch this for TV as a similar model as the radio model, but we have lots of ideas of what to do next. And the most obvious thing to do is to add more features. Currently we only use the user ID and the kind of the content ID, but we can add stuff like time of day or weekday as part of the context. Also, whether you're on a cell phone or on a big screen can be a context. Also, what type of users, more kind of, if you're a power user or someone who's never visited us before, that's a useful thing to have as part of the context as well. And for each action, each podcast or TV series or something, we can add like things like categories, whether there's a new episode just being published, if it's how long the content is, if it's 5 minutes or an hour, might make a difference. And we also want to add more personalized sections. Now we have only 1 per page. We want to experiment with more reward functions. Now we say that it's a success if the user has consumed 2 minutes of the content, but that's we can experiment with giving different rewards for different type of content, for instance. And also now we do train this in a batch fashion daily, but the WAPL Rabbit supports updating this live, so we can be much faster in reacting to changes in user behavior. So yeah, that was it, I think. So.
Thank you very much. WAPL Rabbit.
Yep.
So yeah, a quick question while Jakob sets up. Kim?
Line. Your name is Line, right?
Linn, Cecilie. Yeah.
Almost, sorry.
Yeah.
When you say that you say that it's a success when somebody clicks on it, and then all the others is a negative example. The items that comes after in the list could be unluckily influenced by those negative clicks, in the sense that have you looked into only saying that it's negative in the products until there, in a sense people read from the left to the right, so if it's the third one, then the fourth one should probably not be negatively.
No, we have not. But I mean, only those that are visible will get a failure. And as Thomas said, basically it's one or maybe three items that are visible at the same time.
Okay.
So
the reason why I'm asking is because you will probably have a popularity bias, because you're pushing the things that are, how do you say, the first ones will always go further to the left than things behind it.
Yeah.
Yes.
Yeah.
Yeah, but we have information on what is visible. Yeah, okay, yeah.
But there's a connection set up, so please
Hello, everyone. Nice crowd. So yeah, I work in Curate, primarily work with news recommendations and personalization. And today I'm going to talk about some of the discoveries and lessons that we have learned within Curate with respect to personalization. But before that, I would like to give a brief introduction to what Curate actually is. So Curate is a central team within Schibsted that is available for all Schibsted and Polaris newsbrands, regardless of size or reach. So in collaboration with the brands, we utilize automation to recommend content on front pages. And we do this by supplying a set of tools that can be used by the news brands with the aim to increase both their user engagement but also conversions. But in the same time, we want to preserve this journalistic mission to actually get the important news out there. So Curate's product can be categorized into two main services. The first one being this front page manager, which enables news editors to pick which stories they want to pick in various positions on the front page. But when dealing with this constant stream of news articles being published, this manual curation becomes quite impractical. So to address this, we have provided this customizable ranking formulas to allow each brand to customize their own specific front page. So to illustrate this, we can consider this as a quite rather simple ranking formula that we can create. So this can consist of 1/3 of time decay to reflect the recency of the article, 1/3 of live ETR to optimize the click-through rate, and 1/3 of popularity, so mainly clicks. And this is for the goal of engagement. But you could also do another ranking formula that focuses on conversions instead. So you're kind of breaking up the different optimization goals here. So the possibilities here are quite endless, and the end result will be a list of articles that both consist of manual and automated content with different goals. And this is also highly customizable, so you can pick either fully automated or only secure positions, more or less. However, in recent years, there have been this significant increase of personalization, the reason why we are here today. So now imagine if we can add 20% of personalization to this regular sorting of articles. So a few years ago, we started on this ranking called Sporty Elephant as one of our first attempts in personalization. This was many years ago. But the basic concept was that sport contents either make the readers highly engaged or not interested at all, right? And the idea was to calculate this sport ratio. It's more or less the ratio of total clicked articles on the sports sections. And then together with some statistical calculations, we would determine how much sport we would give to the user, right? However, this ranking had a quite missing component, as it didn't take the exposure into account. So it only looked at the clicks, but not the impressions, right? So it wouldn't really distinguish if the user had been seen or exposed to 3 sport articles or 100. right? And as well as the sport content varied over time. So let's take an example like VM or the FIFA Cup, then you will have been exposed to a lot of sports and you will probably be more likely to click on it. But if we do not include that to the model, it will kind of overestimate or underestimate the preference of that section. So to address this, our team implemented this algorithm that takes both the user clicks but also the impressions into account. And as you can see, it's quite similar to NRK. We do the success as a click, but then as a failure, we do the impressions minus the clicks instead. And this allows us to calculate this user interest probability in each section and then rank them accordingly. And here it's up to each news brand to decide which sections to include for personalization, as maybe not all sections should be actually personalized. However, it's quite important to note that this topic ranker, that we call it, has some limitations. It only looks at one user preference at a time, and it does not really consider this user-to-user interest, like common interest. And it's also is specialized on topics, not on these specific articles. But something that we could use to get this more fine detailed personalization is, of course, collaborative filtering or matrix factorization, which I think most of you are familiar with. But if not, quick recap. So given that we have this R matrix, where the user on the rows and the articles on the columns, where each element consists of observed data from our users, so in our case, a click, then we can learn this latent representation, so the U matrix or the V matrix, where each row will be a user and each column in the V matrix will be an article, right? And then you can make prediction on an unknown item for the user. And here the thing is that collaborative filtering is one of the most popular approaches used in personalization in many domains, but to my knowledge, it's not too widely used in the news domain, nor in the literature in the news. So Curate and other teams within Ships have explored the use of these matrix factorization models, but the results have been quite mixed, right? At least for the news domain. But if we take a step back and actually look at the ways to train these models, so for instance, alternating least squared or negative sampling, they both share this common assumption when defining the likelihood. And this can be referred to as the all-item likelihood. So it assumes that all items has been available for the user at all time, but it also assumes that the items has been exposed to the user uniformly, which is kind of not true. And this, so with negative sampling, for instance, you will actually feed the model pairwise observations. So one positive and one negative to just explore this. So we will know the positives in terms of clicks from the user, but traditionally, at least for the negative sampling, you will draw a random negative item to explore this matrix or to express the lack of preference by the user for that sample item. But maybe a more realistic approach is now to actually look what the user didn't like, right? And as we have this impression data available, we can actually do this. So instead of sampling just at random, we can go into the impression data and say, okay, this user didn't click on this, and we'll sample that. And this is what the slate likelihood does. So it will go over, instead of n users and m articles, it will go over the n users, but only the articles that was observed in the user session. So in a master thesis I did last year, using Aftonbladet's data, we compared two collaborative filtering models with this setup. And what we could see was that when we were using this traditional all-item likelihood, it would perform worse or in par with some weak baselines such as random, decay pop, and recency. But when we use this in slate likelihood or slate likelihood, it kind of outperformed the traditional all-item likelihood by quite a lot. And our hypothesis why this might be the case is that this slate sampling strategy seems to handle both the exposure bias, but also the popularity bias, which is very prominent in the news domain. And also we think that it's also related to this all item likelihood being more suitable for item spaces or large item spaces such as marketplaces where news domain has far less items. So you're more likely to be exposed to items. Right? So it seems that we have found this sampling strategy that works for our purpose. However, two problems still remains when doing recommendations, of course. The first one being these common co-star problems. So let's take the second item, the music item, where we have few user interactions. Then we won't be able to learn the item embedding for that article, right? And the second problem would be if a new article is published, then we won't be able to make any recommendations. However, imagine now if we can actually introduce some prior knowledge to this V-matrix that does not require any user clicks. And this can be done through NLP, where we use something called paragraph representations or doc2vec. So for each article in our training data, we would simply feed in the text data to learn these similarities. And then we can actually put this theta as the prior mean for the item matrix. And what this does is, skip ahead. So by doing these articles with few interactions, we rely more on the text representations. And as the number of interactions gradually increase over time, it will rely more on the interactions. As we saw the quote from before, that interactions from the user are more valuable than metadata. And we can also control how much we should actually rely on this text representation by this lambda term. So it's simply L2 regularization. And with this setup, you can make two types of predictions. So either U times V, so the in matrix when you have clicks, or U times theta when you have no clicks. So when we introduce this NLP component as start weights, we could see that the model uncertainty in terms of co-star problem would actually decrease. So now we're really excited about trying to get this to production in the coming months. And if you're interested in talking about these kind of problems in day-to-day life, please contact me. Thank you for listening.
Thank you very much. Any questions? Yes?
Thanks for your talk. It was interesting to me that you mentioned popularity bias. Do news articles have enough of a lifetime to have prominent popularity bias?
It depends. We have something called evergreens that are articles that kind of lives for longer time, which will have a popularity bias, yes.
Yes, Johannes from Ekstra Bladet. Just a quick question for when you said sampling from the negative, was that throughout the user's history or just that single one?
Just the session.
Just that session?
Yeah.
So throughout, if I click on 5, it's all the negative within those 5 page views?
Yeah, correct.
Okay.
So we're kind of assuming that all the events are independent in the session.
No, then there'll be a lot of duplicate, or might be a lot of duplicate.
Yeah, yeah.
I guess you remove them.
Not in this thesis, no.
Yes, I have time for one more, if anyone. No? Then, thank you, Jakob.
Thank you.
So, hi. VG, it's Norway's largest digital newspaper. And what I want to tell you about is how we approach personalization on our site. And also a bit about the unique opportunities we have. But let me set the stage for you. We do most of our personalization on the front page. We have a lot of new articles and videos that we publish every day. Daily numbers, we have around 1 million logged in users, which is the target for the personalization. We have around 12 million daily clicks and 213 million daily teaser impressions. A teaser impression is just, I viewed one of these teasers. It's like the sell-in for a video or an article teaser.
this high volume means that we have a very unique opportunity, which is that the amount of time you have from you have an idea to testing it in the real world is really short. And this also sets the terms for how we set our technical rig. So we're always thinking about experimentation first. Yeah. But so, what do we actually do today? It's two things. The first is something called retargeting. We call it retargeting. I'll explain that. So up on the right here, you see a box encircled in red. It's a game called Ordstjernen, where you try to find words, sort of like a crossword puzzle. And there was a dev who created this from a 10% project. And we used it to like make people log in. And so a problem was that it never reached very high peaks of traffic, but it has some really hardcore users. So customer service was sort of flooded with the people not getting the last word. And they communicated with the developer. Our chief editor was really obsessed with this. But then we borrowed this thing from marketing, right? Retargeting. You Google something, you're shown ads for that all the time because your previous interest indicates what's being shown to you. So we made this database of sort of user actions and states. And then if you played it the last 7 days, you get this box. And then sometimes you show it to everyone to sort of get in new users. So that's like a nice compromise to use less space on the front page. So this is really vanilla, and the pros of this setup is that it's really transparent. You know exactly what is being shown to whom, and you're not replacing any content. But we do another thing, which is more in this thing, which is content recommendation. And that's basically replacing teasers. So the way it works is that you load the front page, and some model provides an item list, articles and videos. And then we have some logic, which is like, have you clicked this before? Have you scrolled by it many times? And we change the sorting based on that information. And finally, we replace the teaser on load. So if you load vg.no and then you scroll down really quickly, you might see the glitch in the matrix where sort of all the stories are exchanged. Right. So I'll restrict myself to talking about this type of personalization further going forward. So we have some challenges which we face doing this. First is, Jakob was talking a bit about these things. With the journalistic mission, basically not all content is eligible for personalization. Examples include breaking news, and sports might sound like a really good category to personalize, but then the World Cup in Qatar comes, and you have all like 20, 30 stories in a week about sports washing, which is sort of, the journalistic mission is to put this as an order of business for everyone. And so it sort of interferes in that way. And you'd be surprised, even like celebrity news has this type of aspect to it. Second thing, editorial control is sort of, and I can't overstate how important this is, that you have a good working relationship with the editorial. There are content moderators, and so they need feedback on what is being shown, how much, and how does the system work, and what kind of control do I have to change something like that. I'll give you an example of that afterwards. Also, our business model is called freemium. So it basically means that like the revenue we get that pays for the journalists that make the stories is based on showing people ads, it's selling subscriptions, and it's affiliate. Affiliate is sort of like you press on a story about fashion, there are products which link onto some site where you sell the products, and you get a percentage of that. And so point being that should you optimize for subscriptions sold, ads shown, they sort of cannibalize off of each other. So it's not like straightforward. Our approach is kind of conservative. It's limit us to a specific domain, VG+, sell subscriptions. So exchange VG+ teasers on the front. Or niche stuff, consumer stuff, stories about fashion or food or tests of technical stuff. And also a bit of video content that we have. We've done most of our work on VG+, but even though we limit the domain, we still have challenges. This is the Minister of Trade and Industry in Norway. He's holding a clock, and the story is about daylight savings and was published on Sunday. And then Monday came along, and our models, this was a nice story. So a lot of people were confused about if they should set the clock again. So, yeah. Another example, this was an investigative story, which was sort of not deemed that important for everyone to see. So after having at the top of the front for 2 hours, they hid it behind paywall. But then we personalized on it. And so some of the models that were in play are not have this cold start issue. So to the front editors, it just like vanished into a black hole and never came out again. And their intention was to like, this is a really great story. Now you want to show this to everyone and sell subscriptions. And so this is coming back to this editorial control part, where the analyst is then telling the front editor, which is despairing over the vanishing story, that you can turn it off if you'd like. You do it like this. It's pretty simple. Of course, we work on fixing the cold start issues. Right, so cold start because it was open, so it of course didn't have any sales. It was closed. Well, then it's prioritized low because it's been exposed a lot but doesn't have any sales. So it's a yeah, poor story. A bit about our models, just an overview. I mean, we started out doing a lot of list models like most read or most read within a certain demographic, or presenting this to everyone, which has clear biases. And we've only recently started venturing into like the Rexis world, where we have, and this is an example where we've created an offline data set based on the same like exposures and clicks and how long did the click last for and so on. And in this case, we trained a model that was optimized for selling subscriptions. So did this impression lead to a subscription? And if you shuffle them around, do you increase the probability of selling a subscription? That was sort of the job of the data. And not going into very much detail here, but the different approaches we try, they work, but we don't have like a silver bullet for one thing, like one model works in optimizing sales, but maybe users are a bit more put off, like they leave the articles very quickly. Another model is really great for the reading rate. I mean, you go in, if you're exposed to something, you're interested in it, and you have a subscription, so you read it. But we don't have like a silver bullet for the whole thing. That's our current experience. But I'd like to go a bit back to what I said in the beginning and talk a bit about this experimentation first thing and tell you about how we're set up. So it's like a very modular design. We have a model API which serves the expected output of the model API is that per user ID, you get a list of items. And you can basically plug in any model that returns this, and our brain will just push it onwards onto the front. And if you open that red little box, it's not only the front page, but it's also like a very modular system, which is the reader history is cached, real time, the feeds that the models are, or the list of items that the users get are cached, and everything is sort of very modular. And we like to think of this as sort of we have a great racetrack for experimentation and testing. And if someone wants to come try the racetrack, they only need to produce something like this. And you see also there's a box called Curate, which is what Jakob just talked about. Because Curate, they created an API, which is per user, what's a list. And so it's really cool. We can sort of use our front page to test like which models perform how well. And that's really a core part of our philosophy. We always want to be experimenting. Right. Thank you.
Thank you very much, Johannes. Any questions? No, everything was crystal clear.
Right.
That's
one quick question.
Yeah.
Just out of curiosity, what is the response time for the models?
The response time for like...
for a model to be valid in your setup, like for a user coming in, getting a request.
So everything is cached, so it's like the loading time of the teasers. So it's instant. Yeah.
Right.
Yeah. We don't do it for the top when you load the page because you get a flicker on some stories. So you have to scroll down really fast to see this. But yeah, that's basically what's happening. You're assigned model, list, check user read history, and then replace teaser. It's like milliseconds. Yeah.
Great.
Right.
Thank you very much, Johannes.
Thank you.
All right. Everyone can hear me loud and clear? Excellent. All right. I'm Johannes. I come from Ekstra Bladet in Denmark. And I'm here to tell you a little about the journey we've been on. So, first of all, here's a quick agenda. I'll tell you a little bit about Ekstra Bladet. I don't think everyone is familiar with us necessarily. Then about the project I'm working on. So I can quickly introduce myself. I'm an industrial PhD student at Ekstra Bladet working at the Technical University of Denmark as well. So I'm in both places. So I work on this project, Platform Intelligent News. Then I'll tell about the recommendations at Ekstra Bladet. For this audience, I think you would be interested in some A/B testing and some of the results we had, and a teaser for what's coming. So quickly about Ekstra Bladet. It's a Danish tabloid newspaper. It was founded way back. It's published by JP Politikken. We are around 200 employees at Ekstra Bladet. We are right now the #1 most visited news media publisher in Denmark, according to Similar Web. We have around 1 million daily users, unique IDs, and then we have around 450 million plus page views per month. So we have some traffic coming in. So as I said, I work on a project called Platform Intelligent News. It's a collaboration between 3 of the universities in Denmark, where we do all kind of stuff. So over here on the right, you can see some of the stuff going on. At Ekstra Bladet, we're around 5 ML specialists in-house team working together with 2 industrial PhD students. And the project is Ekstra Bladet is paying some of it, and then we have a grant from Innovation Fund Denmark. I work with recommender systems, so even though we do a lot of other stuff, I'll focus on this one. But if you're interested in the NLP stuff and all that, we're also doing a lot of that. All right. So I like to say that what we do at Ekstra Bladet is like Netflix, but it's not like Netflix. For some of you, so Ekstra Bladet is a Danish news publisher. So some of the challenges we face in news recommendation is that articles are being published continuously, and they are published very fast, and the relevance of these articles is usually quite short. So severe cold start problem, if you want to say it like that. The user interest can shift very fast, like in the morning, in the afternoon, maybe there's a sport event, maybe there's an election going on. As I said, interest can shift quickly. Then, because we only have clicks, we don't know if people really like what they got. But it's the best we have. At least we don't ask them directly whether they like it or not. So it's implicit feedback. This goes, it's getting a lot better, but Danish is kind of low resource language compared to English. So some of the NLP techniques out there they're good in Danish, but definitely better in English. Oh, and an important one. At Ekstra Bladet, we also have this alignment with editorial values and what the systems can do. A term that we start calling normative thinking. So not just thinking about the output of the model, but thinking what should the output be according to our values. All right, so quickly, what are the panes at Ekstra Bladet? So we have a front page. This is just a screenshot zoomed out, where news is being published. This is editors putting stuff on that. We publish around 200 to 300 articles a day, and we can't fit that much in there. Second, so people will miss a lot of the articles being published because we can't fit all of it in there. Second, right now people tend to read an article and go back to the front page, meaning that we can't show you more stuff because you're back at the front page. So that's the second pane. So so what we're trying to do is we'll introduce recommendations. You can see these horizontal lines where we're starting to introduce personalized recommendations. So we're not changing the DNA or the standard as a person might know it, but we're introducing some recommendations in your news flow. We're also introducing some similarities when you've read something. That's another feature. This is not necessarily recommenders driven, but it's similarity of NLP in the end of an article. All right. So what are the goals of the PIN project? So for me, here's one of them. We want a wider scope. So we want you to discover more news, introducing these personalized in your news flow. And we want to allow the user to delve into an article. So once you've read something about the Prime Minister, maybe there's more articles about her you want to read about, as you saw with the similarity. We want to put normative thinking on the agenda, meaning that we want to highlight the importance of editors' values, the alignment between a company and the systems that they put out. And of course, it's a company. We have some KPIs. The board would like to see us do better in all aspects. We want more page views for the free stuff, more page views for the paid stuff, and we want people to start paying for it. So pretty easy. We're going to solve all of them. We've done a lot of offline testing, all that. I'm very much a technical person. In this presentation, I won't go very technical, but please come, ask me about any of it, and I can spend 10 minutes extra on just the technical stuff. So some of the results. So I would say this is probably the easier results getting, meaning that a year and a half ago, we didn't have any recommendation systems. So we're pretty much beating just like manually the editors, the humans, like not trying to beat the supercomputers. So next one will be even harder to beat these scores. But we got really good results. We implemented it as you saw before. And just on the first KPI, on the free stuff, we had a factor of 2.7 increase. On the paid stuff, here we've segmented into different user categories. Ask me questions afterwards if you want to know more about the segments. But we also saw a great improvement implementing these models. So for example, for the loyals, we had a big increase. All around, we had a big increase. And same goes for sales. So for the loyal users and the logged-in users, so you can have a login without having a subscription. So just to clarify that. So for the logged-in, using this method, we also saw an increase in sale. So everyone was happy. So you can ask yourself, did it work? We at Ekstra Bladet think it very much did so. So this is one of the case studies we have done. So you could also ask, could we have pushed it even harder and had more, increased even more sales? We probably could, but that's where the alignment come in. Instead of just thinking we want to sell the most, we want to sell more, but we want to have that aligned with the editorial values. That could be that you want to limit the type of news that you recommend. You don't want to recommend necessarily just slaughter and like something, if a murder goes on or something like that can bring engagement, you don't necessarily want to promote that. So we have limited the type of news that we recommend. We also ask for acceptance for the users, whether they want recommendations. Like we try to constrain models. We're aware of filter bubbles and all that. We're aware of it, so we look into it. We're not really generating any filter bubbles. I think this sentence, like constrained model training. We have constrained model training, and we are aware of it. We don't want to create filter bubbles, and I don't think it's necessarily something going on at Ekstra Bladet. No, it is not something going on. These are some of the things that you could have as values. We learned a lot during this process. So this is actually what we did last year. We're doing a new run this year. So this was the first one. Don't necessarily do what the tech giants do. They might implement something, come out with an algorithm. That might not work for you. There is no recommender to rule them all. Simple as that. We don't see, for example, collaborative filtering might have popularity bias. We don't see that as a bug. We see that as a feature. So learn the algorithm. What can they do and what are they good at? And then implement them the right places for the right people. New technology comes available. Transformers. I think I'm almost running out of time. No? All right. With new technology coming up, you need to stay ahead of us as well. We had quality review, meaning that we tested the recommenders on ourselves. We had a setup where we could test what are the actual output, not just the metrics, because those two are two very different things. We had one model that performed very good in an AUC, but the quality of the, how it did, the experience of it was really bad. It basically just recommended the same thing for everyone, which was kind of an interesting finding. So it's really important to actually check it yourself. And then putting this into production is just goddamn hard. It's not that easy. We try to put the norm setting on the agenda. So we tell readers that they're exposed to AI. We had this on for a year, exposed like millions of users, and we had one email about one person was curious about it. So we tell them we think it's important, even though not too many people actually might read it. But we think it's important. We open source the technologies we make, and as a researcher, I'm publishing the results. So we have some things that are already out there. We have, this is just a bit of teasers of stuff going on. We also have some conferences where we put this, try to bring media in to talk about. Quick teaser, what's coming. I'm working on a big data set, so everyone who's hungry for data sets, I'm working on a huge news data set. I hope to publish soon. There's a big conference in Nordic in Media Summit in Copenhagen in May. If you're interested in similar events like this, I would definitely check this out. And then normative thinking is coming on the agenda. It's not, I guess it's official. It's coming out soon. We got the acceptance letter. We have a workshop coming at Rex's 2000 in Singapore this year, but it will be out soon. Yeah, if you have any questions or anything, please come by.
Thank you very much, Johannes. Any questions for Johannes? Yes?
Thank you, Johannes, for a great talk. How do you think about optimizing for like click-through rate versus read time from the user? I'm guessing like click-through rate might give you click rate articles, but read time might give you something different.
Yes, so we're this test round, so we do like, last year we did one, this year we're trying to do on read time as well. to see what effects it will have. The click-through rate is the easy one because it's straight away. We definitely think like you think, but we haven't actually gotten the results yet, if it holds. But we expect something similar.
Yeah, thank you very much for a great talk. So you mentioned actually that you are trying to align with those editorial values, you know,
yes.
the recommender system. Fantastic. Yeah. So first, and I mean, I was wondering, how do you do that? Yeah. So from a written perspective.
Yeah.
So I mean, I've also written an article that will be published this year in Communications of the ACM, where we try to look into those values that editors have, and try to apply them algorithmically. And the figure is actually not so easy. So I was wondering how you do that.
Yeah, we probably have to call my boss. He's the one that does that part of the job. He tells me what I need to implement. I can give you his connection. And so Casper, my boss, he's really good at communicating, and he's been there for a long time. So I'm not quite sure what his strategy is, but it seemed to work.
So you said like don't do like the big tech giants like Netflix.
Not necessarily.
Necessarily, yeah. So, and I guess that also on the modeling side. So you're using slightly different models than what you see. And can you talk about a little bit what kind of modifications or what kind of models do you have to use?
So we actually started off being very explorative. So we tried to just look what's out there and take what the tech giants have made and test them out. So we didn't pick one, we took all of them that were available. And for our use cases and segments, we started to like notice some models might have different properties. So we're still using models produced by, for example, Microsoft or something, but we're applying it in an Ekstra Bladet setting. Yeah, I don't know if that answers.
You had a quick question? Oh, it was just a comment on the read time and click rate. Just that read time, in our experience, is not that. The important thing is the quick exit rate. So, because read time is not that sensitive to quick exit percentages.
Yeah, I think we try to filter out noise, and we think that the bounce, the quick exit is a big noise factor. You clicked on something and you left it like within a second. It's probably not a good education.
Perfect. Thank you very much, Johannes. Perfect. So now that I am the number 3 or 4 news media company that's going to talk about recommendations, I think there's not a lot to say, actually. So brace yourself. I'm going to say a lot of things one more time. Right. Okay. So hey, I'm Ludwig. I'm a product manager at Aftonbladet. I'm part of one of the teams that do development for Aftonbladet, which is Sweden's biggest newspaper. And my team is the team that focuses on user engagement, personalization, video, and some other stuff, which essentially relates a lot to whatever we do on the front page. So, as I said, I'm going to talk about how we break down personalization in a newsroom. Why do we need to personalize the front page, what it means to us, and how we are doing it. I'm going to start with why. So, people come to us as a primary news destination for different purposes. They come either to get updated on the current or latest news situation. Maybe they're on the bus or on the subway, they want to get entertained, they want to surf around, or they want to find something to talk about with their friends, family, or colleagues, or something else. Our users are in many different contexts that visits us. That's one thing we can know for sure. Also, we win. We have the most unique visitors. But I don't think we had more weekly published articles than Ekstra Bladet. But we have more than 3 million daily visitors, and we publish 1,000 articles every week. And essentially, this means that we speak to all of Sweden on a couple of days, during a couple of days. And of course, Sweden is not homogeneous. Sweden has many different people. So fulfilling the tasks of updating and entertaining people is very tricky, especially when you publish one new article every 10 minutes. And people don't come to us every 10 minutes. We have it looks like this actually for a week. People do come to us very often, and we're very lucky to have it like that way. Because in 16 hours, 50% of our weekly users visit us, which is quite amazing. But that still doesn't cover the fact that we publish one article every 10 minutes. So we are too slow. Or our users are too slow, maybe I should say, to visit us. And then we had the third thing. We have talked about this before. We try to drive many different business, or many different aspects, I will say, on our product. We have the journalistic mission. It's the most important thing. We're not owned by the government, but we still feel the same responsibility to contribute to society as, I would say, SVT or whatever in Sweden do feel. We have ads, of course, because we are not the government. And then and then we have, we want to drive engagement. We want to make people happy. We want to, like, they come to us on the subway, and we want to make them, like, you should be able to spend a minute, find something nice to rest your eyes on. Maybe this is not the best example of that, actually, now that I think on it. But we try to drive engagement. And then, of course, we want to sell subscriptions also. We lock our most, or our best journalistic content, we lock behind subscriptions. So all of this we try to drive. We also have the affiliate and many other new types of things we want to drive. So the front page is very crowded. Enter the holy answer, personalization. We serve a very diverse crowd of people. We produce more content than we're able to show to each user. We try to promote different things on our front page, and users have different interest in these things. So personalization should answer up pretty well to that. We should be able to give the right content to the right user. Looking from another perspective, personalization helps us remove content users have already read or seen. It helps us promote content that is more relevant for users, but also actually remove content that isn't relevant for some other users. And in addition, and NRK talked about this as well, we also pair it up with segmentation and actual general optimization to boost the personalization efforts as well. So this is an illustrative picture showing how personalization moves content up to the top of the site where users are. Or actually not at top, but higher up. Do you want to guess what I'm going to talk about now? Filter bubbles, yes. There is a risk with the filter bubbles. So when you personalize a news destination, you have there's always a risk that we lose our main objective, contributing with information to the society or to citizens for like whatever we need for the democracy to work. And because of this, and this is new, you haven't heard this before, we have a strategy actually in place for how to personalize with you. And I'm just going to show you the framework and give you some hints because I don't want to show the whole thing. But essentially, this is how we discuss and how we personalize content. It's not a do not kind of thing. It's a this is not a problem until like no, big no. And then there's a lot of things in the middle, which is it works under certain conditions. And this is a discussion that we have with the leadership team on a regular basis, actually. I mean, it was a lot of discussion in the beginning, of course, because we hadn't like classified everything. But this is still an ongoing discussion. It's probably never gonna end. And we have editorial representatives in that discussion at all times. So in these discussions, we decide not only the content and how we feel about personalizing or segmenting that content for the best of the user. We also decide what placements that are personalized that gets the most exposure. We talk about what purposes and what business areas we drive personalization for. And our best placements on the site are actually reserved for what everyone should see, what everyone needs to know. And it's gonna stay that way. We don't intend to change it. It also has some nice technical implications because we have to cache our site. So we save a lot of performance due to caching as well. But it's really for the journalistic mission. So as a general rule, I mean, I don't have to say this to this room, but or I will say this to the room anyway. It's like we don't personalize content that infer harmful bias or bubbles in our news delivery. For instance, we don't segment news or any of that kind in like gender or age because we don't want to accidentally send all news related to shoes to women and then like war to men or whatever it may be. And this is part, like it's one of our like principles for personalization. So allow me to demonstrate with a picture what we do when we personalize. Here, ChatGPT, poke it with stick, earn money. That's how you do it, right? No, that's not really what we do. Jakob showed you how Curate works. This is Curate with other images. What we take is the full corpus of articles, and then we rank them based on different business goals. You remember I said we had a couple of different business goals. You have the top positions way up here that are always the most important news for the readers to see. We have conversion ranker, which drives subscriptions. We have engagement rankers, which drives clicks and engagement to articles, and then secured positions, which is because you can't only reserve the top of the site and then have a lot of engagement rankers. You actually have to split up and get more like editorially selected content down on the sites also, because otherwise you're gonna get like news, cats, or something along those lines. You have to mix it up. Jakob never showed this, so I'm gonna steal this from him. It's essentially how we calculate the interest of each piece of content for a specific user in Curate. He told you about different kind of rankers. He told you about time decay, because content isn't relevant always for a really long time. He also told you about conversion ranking, converting based on how well, ranking based on how well an article is converting. Some other things, and you move along to the right here, and then we find the personalized factors here. You have the remove after read, remove after seen. Those are quite simple. If you've seen a couple of things too many times, or if you have already read it, we remove it for the user. But the topic interest is what Jakob was describing. So what happens is we take all of these scores, we put some weights to it, say time decay. This has weight 3, so it's really important. We take live VTR. This is essentially a click ranker, so it takes a weight 1. We add those scores for this in general. We move over here. We add the personalized score, which has a weight of 2. And then we divide it by the total weight, and then you have a rank for this specific user. So this decides the list of personalized articles that you get. Is it working? Yeah, it does, actually. It's really well. We're going from a place where we have an optimized feed, meaning that we are optimizing for the whole. So we went from a state where we were quite performant already. Even so, our sales went up with 40% when we introduced the personalization. I don't need those 2 minutes. I'm actually done. Thank you.
Sauce of recommendation that popularity based is good enough for almost everyone. So if you would just take the popularity stuff and only remove things that users have seen and so on, how much improvement does the entire thing add on top of that?
Not that much, because the popularity. Remember, I said we have the reserved placements on the top. Popularity doesn't take in, or the way I interpret popularity is that it doesn't take into account the exposure of an article. So the one on the top, everyone has seen, so it has a lot of exposures. So it's also always going to be the most popular. It's a exponentially decreasing curve of exposures on the front page. So the top, I think, 10 or 15 positions is 80% of our exposure.
That's the long tail.
Yes, exactly.
20% account for 80%. But so how much, all of your extra secret sauce, how much do you gain by having that, as opposed to only having?
I don't remember the jump from popularity into live VTR. I'm gonna say 20% because that's what I can remember. But I wouldn't take take me too serious on that. It was a lift. It was 20%.
We see that.
Yeah. Okay. Great.
We had a question here as well. Yeah. How you capture engagement? For example, click is one thing, but scroll length or clicking further on the links.
Yes, we take clicks actually. Click-through rate is engagement or measurement for engagement right now. But we're not locked to that. It's what we currently do to measure engagement, but we're not locked to it. We can actually change that goal value as we want to, which is the nice thing with Curate.
Thank you, Ludwig.
So this morning, when Alain saw the program, he predicted that half of you would be outside drinking beers now and the other half would be asleep. So thank you for all being here and awake. Let's see if I can... Don't allow. Okay, there is a clicker somewhere. Okay, I'm standing here. So we all talk about personalization today, and I'm going to continue on that. But I'm going to ask a little bit, what is it also? Because it's good that we have the metrics and we talk about now we personalize and how successful we are with clicks and so on. So I just want to bring it down to earth a little bit and then talk specifically about what personalization is. And maybe I will succeed, or maybe you'll go away and say that there was a better presentation talking about personalization already. I do not come from Spotify. I just want to make it clear. I come from Shopify, which is an e-commerce website where if you have a store you want to put online, then we're there. We have... I have a lot of colleagues, none of them in Denmark. We have around 2 million stores, so yeah, we have a lot of data to look at. I gave this presentation to a kind colleague that lives in San Francisco, so he was still awake when I was finished with it, and he said, it's a good presentation, but what is it that you actually talk about? And so I just wanted to put in the way we understand evaluation. And basically the presentation has come together answering questions on Slack over the last couple of months, because even if I'm not allowed to talk about what we're doing at Shopify, then we are looking into personalization. And I wanted just to put in a quick personalization, or 2 examples of personalizations. So I have access to ChatGPT, and which is a lot of fun. And then people post all over the place how good it is, and so I said good books on recommender systems, and it then came with a long list of things, and they're good books. I tried it 3-4 times because I didn't like the answers that much. Then I said, but listen, I think my book is good. And then I asked it again, and it said, oh, you know what? Let me recommend you this one. And I think that that's a great example of personalization. It did exactly what I wanted it to. It does make me worry about the quality of the output that people are posting around, because it seems quite easy to manipulate into what it is that I wanted to do. Anyway, so what is personalization? I'm not talking about news. I'm talking about, so we don't have one website. We have around 2, maybe 3 million different websites. And so we are kind of abstracted even further away from what it is actually we want to do. ChatGPT said e-commerce personalization is customizing product features, pricing, and so on. I don't know about the pricing one, so some people get it more expensive than others. I don't know. That's not what we do, at least. Some people say that if you ask them what is personalization, they say, oh, but we show different things to different users. So that means that if I take these 3 products and then I shuffle them around, then I'm actually doing personalization. Or what? Is that personalized? To be completely honest, I don't know which of these 2 I think is personalized to me, at least. So, and this is the slide that I thought, I came this morning and I actually had finished it already, and I thought that, oh God, people would have defined what personalization is 1,000,000 times before I came here. But nobody did, so this is the first definition of personalization of the day. Imagine that. And I think that, so I came up with 2 things that I want to focus on with personalization. Is if a user arrives somewhere and is looking for something specific, then personalization is to find it fast. On the other hand, personalization is also about teaching what products or content. Since I'm in a product world, so I'm trying to be general and say content, but product slips in every now and then. And so try to teach what the user wants, but just didn't know it yet. Does that make sense? Sleeping? No? Okay, good. Okay, so if we think about helping the user, and you can exchange this with articles or music songs or films or something, then basically what we have is that we have a session where the user interacts with something. We have a few clicks, and then after a while, hopefully there is a conversion. Conversion, again, could be that we read something, we bought something, or we signed up for a newsletter. The thing is that if we should also look at the monetization of things, is that if we want to personalize things, it's also worth remembering that, oh, okay, this is in the wrong end. Anyway, that when we start over here, then we have a lot of customers. The chance that they actually stick around long enough, and we're talking seconds here to the next click, is smaller and smaller and smaller. So it's great to have browsers, but most of the customers that we know about, they have really short sessions, and then they move on to the next place. So do I have a slide later on saying that? So it's very important for us to actually be sure that we have the conversions as fast as possible also. So one way of defining how do we do personalization is to say, based on a few clicks, then we can actually push what they finally buy much earlier into the session. But then we should again remember, because if we can then predict, again, now if you're not awake, then I was talking about the game controller. Then we have all this real estate, and we just had a few items in the top. In a sense, mostly we don't know really a lot about the users, especially in an e-commerce setting where people are not kind enough to log in. I hope you have more data about them. But then we have all this other real estate where it's actually really a good idea to use it to teach them about other things that they can look at. And this is where some things and some recommenders actually go a little bit the wrong way. Because if we, again, I'm talking about sessions where we didn't know much about the user before, or probably nothing, and we just have 2 clicks. That means that this model will produce something that is probably a point in a Latin space or something similar. And then it will find products that are similar to that point in the Latin space. And often you end up with a recommender system that will just show game controllers in different colors, because those ones are the ones that are closest to what we know about already. And this is why I'm saying, watch out, because here you can actually gain things. And then I also wanted to say 1 second, because in our project, I have the pleasure in my position. I'm a recommender engineer, by the way. I came up with that title myself, and I think, as far as I know, I'm the only one ever to be that. We have a lot of discussions about, oh, well, we'll just put on personalization, and then everything will work better, right? I've seen drafts for projects where we will say, okay, we will have 10% increase in our GMV, which is the gross gross merchant value, because we add personalization. All right, I think that's great. But then we have the problem that we don't know nothing about most of our users, so how can we actually do personalization when we don't know anything? And here's where you could then say, is it then worse to start doing personalization, or is it just best to say, I'm just going to do add the most popular products because those are the most safe bets. Then you can talk about demographics, country, time of day, and so on, and then you can start narrowing it down. My experience in other places is that if you look at different cities outside of cities and countries, there are differences in what is more popular in those demographics, and it's worth doing. And then, of course, as you have more interactions, then it's time to start personalizing. But those poor algorithms, wait with using them until you actually have some more data, because otherwise they won't be good. And then I wanted to talk a little bit about how we actually do the evaluation now that we're all clear on what personalization is. Because if you don't know how to measure it, then you don't know how to evaluate it. So if you go back to that session again and say, we know that these are the clicks right now, so basically try to simulate what is the environment where our poor robot or agent has to battle its way towards the attention of the people, and say, we know this, we tell the recommender, we have these 2 clicks now, could you please give us a recommendation? And here we have this funny thing that we talk about, is the 0-click personalization. And 0-click personalization means that you can already, when they arrive, have the IP address and whether it's a mobile device and so on. And your model should either be able to do something about it, or you go back to the popularized popularity metrics, models. It provides a model. And then it's important to think that in the evaluation, we actually don't know what came in. We only want to see the output, and then whether it's a success or not. That's also something that is very important to see, that the evaluation is model agnostic. So it's important that you don't try and somehow feed what you put into the model into the evaluation also. At least if you want to compare 2 models apart. And then I just wanted to make out, I think I said that already, no data means no personalization. And then one of the things that we talk a lot about when we talk in research, and also this model is better and this model is worse, is these ranking metrics, or metrics in general. So mean, average, precision is a ranking metric. So that means that, is that the next slide? No, it's not the next slide. That it values a recommendation better where the product that we are looking for higher if it's higher, and so on and so on. While the hit rate just says, this is what the user saw, was there a hit or not? What I see is important is that the hit rate is actually the one that, from my point of view and from most users, are actually important, is that when you get a screen and you see a slate of things or you see a list of news, then you just want something to click on. And then they will probably come back and click on something else. But it's only important that you have at least one item to start up that will make them click. So whether it's, one of my colleagues call it, I can sort with my eyes. And of course, if you have a page where there are 50 slates and so on, so if it's down in the right corner, it's a problem. But there is also room for a little bit of how do you say, flexibility, and say, as long as there's something they click up from the beginning, then you're pretty good. And that's actually what the hit rate does. Then you can take the mean average position afterwards and say, oh, I have two models here. I have one team and the other team did another model, and now we're fighting about who should be shown to, or which should be shown to the users. If you don't have multi-arm bandits, that will solve. 1 minute? All right. But there is a coffee break afterwards, right? All right, I'll try and be fast. And then another thing that usually is forgotten in these metrics is the diversity. I don't want to recommend a system that is the 100% in mean average position. I want to recommend a system that shows one click and then teaches me about the diversity of the catalog we have. So that's what I want to see papers on. And just that one number, in a sense, when we talk about A/B testing and multi-arm bandits, we have all these nice distributions, and we say this distribution is better than the other one based on some statistics. When we talk about offline evaluation, we say, we have this number, it's better than this number, and that's better. And if you think that maybe what you could do is actually, you could have 10% that was very happy with the first model, and then we forget about those 10%, and then there are other 10%, or maybe 11% that are happy with the new model, but you lose the other the beginning 10%. And then is that really a more efficient model to have? This was the thing with the math, MAP. Okay, so yeah, okay, so maybe how much time do you have left?
Like 20 seconds.
Okay, 10 seconds. Okay, so session, are they ground truths? Because one of the things that we talk about is that, so if you don't have data on whether a thing has been viewed or not, it's considered a negative example. But remember, the session data or the data that we have is not actually a ground truth because we don't know anything. Then, okay, this one will skip, this will skip. So basically, we have a user who loves these products, but before the old recommender has only showed these two. So if you train the model to be optimized for the old recommender, we'll never figure out whether the user actually loved these ones or something completely outside of the catalog. So it's not a ground truth. It's, how do you say, it's a peek hole into some kind of truth that we will never get, because it might be that the user also changed their mind about 4, 5, and 6 in the meantime, so maybe it's not even worth anything. What I'm saying is just that the data that you got is kind of an inkling, and it can help you to go in one direction. But please don't think that it's ground truth, because that's a mistake. I have this slide, and then I will skip over the rest of them. Then one thing I also wanted to say is that we should remember that we talk about that we should have fairness and we shouldn't discriminate anybody. But as soon as you personalize, then you discriminate, because a discrimination means that you filter things away based on who you are. Think about that. Why do we personalize? That's me.